We welcome our Vice Chancellor, Honorable Vice Chancellor, Professor Shoykot Moitro, whose patronage this FDP Faculty Development Program being held, and we invite him to kindly inaugurate this conference.
Should I start?
Yes, yes.
The title is different tools and techniques of physics for industrial problems.
Yeah, actually, there was a slight modification. I mean, the thing is that the original title was a little different, so there was some problem with the. I think some mismatch what happened in the middle. But then I corrected the title, and now it is back to the original title, which was there. That
Now, what is the exact title then?
the title is Current Topics and Tools of Physics for Engineering, Science and Technology. That was the title given in the flyer.
Current topics in science and technology. এটা ঠিক করতে পারবে? আরে আবার সব সেটআপ ফেটআপ বন্ধ করে বাড়িতে আবার করতে পারবো না কিন্তু। তাহলে কি করে করবে? এটা তো হচ্ছে না দেখছি। এই পাসওয়ার্ড জানি না কি এটা যদি ডেটা থেকে ডিরেক্টলি মানে ট্রান্সফার করে আবার ওটা ভেঙেও গেছে। Okay, so far I understood this topics and tools for applied physics for scientific community or for future science. This is the first type of endeavor taken by our newly established, this programs or new department in natural science, applied science and social science. It was there natural and applied there. Of the late we included social science to make it newly established school. So under this school we have initiated several programs, and one of the future program is now some certain programs in physics. Now in that direction we are trying to build up our own infrastructure and own strength for imparting, teaching and learning and training in physics and related area. We are very happy that Dr. Prabhuddha Sannand, he joined us. He was there at IIT Roorkee perhaps. So we will be getting more faculties in this department to initiate programs in physics. Now the thing is this, understanding this physics and in the context of these tools and techniques and particularly softwares and all these things, it is at present time it is of immense importance. Because of this fact, now these different organizations, they are looking after persons with proper understanding of science and with the right set of skill in different computational techniques and in allied areas. So this blend of this knowledge, theoretical knowledge in physics, some applied part of it, and at the same time some computational tools and techniques are making these applications of these subjects very formidable and very attractive. Personally, my experience is now many multinational organizations, they are also looking forward for persons with very good this grasp in theoretical and applied physics with a this profound competency in different these emerging software tools and techniques, programming languages and tools and techniques. So I believe that we will have different components and different important areas of applied physics deliberated at this 5 days faculty development program, and the resource persons, all who will be presenting their these lectures and their study their notes and their this deliberation. So they are all experts in their own field, and it will be of significant benefit to all the participants. Now I like to remind to all the participants, and this is my habit, I reiterate these things at each and every occasion. This time, this 5-day faculty development program, it is actually, you see, um, uh, an initiation towards this learning and towards getting expertise in certain things. But this is not the end. We have to make it sustainable and we have to take it forward. From university side, we will try to organize faculty development programs in this area, maybe at later stage, taking feedback from you after proper designing all these curriculum and programs. But at the same, your responsibility is, as you have assembled here at digital platforms for faculty development program, this is really challenging. Faculty development program so far, it was happening in physical environment, and the situation is entirely different. You could feel the warmth and this presence of your peer, these teachers, the trainers, and that was this different ecosystem, different system. But in digital atmosphere, here digital platform, you are this sitting isolated and from your and separated from your peer, and you are only this engaged in one-way communications, and looking at the computer screen for a longer time, it is also strenuous. Without any activity, you have to focus on the computer screen, and that is only the source of this communication here. So this, as this is a challenging scenario, and we were the proponent of digital faculty development program long time before, because of the fact that it saves lots of time. Otherwise, we experienced these the things that many times you had to release faculties, because this is our responsibility to train the faculty to arrange facilities for upgradation of them. But most of the times when faculties are out of their classes, the academics, particularly the students, they suffered. So we propose this to MHRT, this UGC, MHRT, and many other places, that if it can be made digital for certain times, then we our academic, this all these systems that does not get hampered. So and we are very happy that after that UGC also declared that digital faculty development program is also this one of the viable option and also one of the accepted option. So and we introduced this digital faculty development program. And this is the only option left right now. We do not have any other option left. So this is the only option left, and we have to take maximum benefit out of it. And they are the concept of self-learning, engaging ourselves in a more meaningful way. This requires lots of practice.
Voice is cut off. Voice is cut off.
This this interesting, attractive, and maybe monotonous. These problems of digital platform is like this: the attention span drops very fast. But our responsibility is to keep our attention span, attention level very this active, and for that we need to have there's lots of self control. So this is my advice to all of these learners here: kindly get yourselves engaged in active learning process. Take notes, make your comments at discussion forum, discussion front, question answer chat box, from all these are there. You can put your comments there. You can, of course, this is related to subject matter, and you can get feedback from all this this your peer, or maybe the trainer, maybe other teachers. They can post answer, they can give their opinion, and in that way we believe that knowledge generation also takes place. So these are all these cultures in the digital platforms for taking this learning process more effective, more engaging, more attractive, and we believe that will be followed here. And I wish all of you a very effective and happy learning. My sincerest thanks to Dr. Prabhuddha Sannal, Dr. R.C. Bhor, Professor Shubhendu Samazdar, and all those who are after this, for these organizations of this faculty development program. For the first times in a subject like physics, we are organizing this faculty development program from this university, as far as my information goes. So it is now a historic occasion, and that's why again I'd like to congratulate all these our faculty members, directors, and HODs for taking this endeavor. And my sincerest thanks to all the resource person experts who are well-known figures in their field for this kindly giving their consent in making themselves present at today's digital platform. This is also another this advantage. Without this lots of time spent and effort spent, we can make ourselves available at digital platform. So we are taking the benefit of all these facilities of digital technology. So I believe that it will be a very useful session. I wish this program a grand success, And at the end, when the program is over, it is my advice to organizer, kindly take a stock how it was, this effective, and what are the feedback of all these participants, make arrangement for their proper assessment, and you design for next level of, this faculty development program in near future. Thank you all.
Thank Professor Shoykot Moitro, our Honorable Vice Chancellor, for his very erudite lecture and comments. And unfortunately, we are very short on time, so we'll directly go to the talks. So the first speaker is Professor Amit Ghoshal from ISAR Kolkata. I will give a brief introduction to Mr. Professor Amit Ghoshal. Just give me a minute. So Professor Amit Ghoshal, he did his PhD in 2001 in theoretical condensed matter physics from the Tata Institute of Fundamental Research. Okay, can you hear me?
Yes, yes, no problem, no problem. Continue.
Yes, yes. So from the Tata Institute of Fundamental Research, and he did his MSc from IIT Kanpur and BSc from Jadavpur University. The topic of his PhD thesis was disorder-driven superconductor insulator transitions in 2 dimensions. So, Professor Amit Ghoshal's employment and research experience is the following: that he was a postdoctoral fellow in McMaster University in Canada from 2000 to 2003, and then he was a research associate at Duke University, Durham, USA from 2003 to 2005, and he was a research associate at University of California, Los Angeles, USA from 2008 to 2013, and then he was from 2005 to 2008, and then he was assistant professor at ISAR Kolkata. He joined as assistant professor at ISAR Kolkata from 2008 to 2013. He was assistant professor, and then from 2013 to 2018 he was associate professor at ISAR Kolkata, and from 2018 to present he is now professor at ISAR Kolkata. And Professor Amit Ghoshal has done scientific services as reviewer for the following journals: Physical Review Letters, Physical Review B, Physical Review E, Europhysics Letters, Journal of Physics Condensed Matter, European Physical Journal B, and Nanotechnology. And he has received the following awards and fellowships. He received in 1995 the General Proficiency Medal from IIT Kanpur. In 2001 to 2003, he got the Sharknet Prize Fellowship from McMaster University, Canada. 2005 to 2008, he got the David Saxon Chair Fellowship in University of California, Los Angeles, USA. And in 2018, he got the APS IUSSTF Professorship Award from American Physical Society. Professor Amit Ghoshal's research interests lie in strongly correlated systems, superconductivity, quantum phase transitions, classical and quantum melting in irregularly confined traps, nanostructures, quantum dots, interference and interaction effects, interplay of strong correlation and impurities in high TC superconductors, competing orders, FFLO phase, vortex lattice metal insulator transition, transition metal chalcogenides, topological phases in presence of disorder. He has so far supervised 5 PhD theses, one of whom, Duti Bhattacharya, is a postdoc at Harvard University. Devmallo Chakraborty is presently a postdoc at Uppsala University. Vishwarup is presently postdoc at Weizmann Institute. Anurag Banerjee, postdoc in CES ACLE. And Anushi Datta is postdoc at CSIC Madrid, Spain, starting fall 2020. And he has also supervised several MSc theses. He has many famous publications in journals of American Physical Society and also in Nature. And also in PNAS, which is Procedure of National Academy of Sciences, and Nature Physics, and is an authority in the area of high TC superconductivity, disorder in high TC superconductivity. And so with these words, I leave the stage for Professor Amit Ghoshal of ISAR Kolkata to give his erudite lecture on this topic.
Okay, thanks, Prabhuto. Thanks so much for such a kind introduction. I just hope I'll be able to do justice through my talk. So I will go forward. But before that, let me thank you as well as Professor Maitra, Professor Bhar, and Professor,
Samadar.
uh, sorry?
Professor Samadar.
Professor Samasdar, for having me here. This is a great opportunity, and this will be a fantastic learning opportunity for me to interact with you guys as well as the students. So thanks so much for this opportunity. Okay, so with that, let me go and start presenting. So let's see. Uh, and as I said, it's a little sad that that even though we are next door neighbors, we are sort of forced to do it through online platform, which is a fantastic platform though, and which has a lot of promise as mentioned by Professor Maitra. So let me check whether this is all good. So let me do a slide show. Uh, slide show. Sorry. Can you see it?
Yes, yes, it's visible.
Okay, it's visible. Okay. So now let me. So there is this thing which I have to get rid of somehow. Okay. Okay. Fantastic. So it's done. Okay, so good afternoon, everybody. So the title of my talk, as written, I mean, so this is the title. Broad title was because I'll be presenting two lectures. So the broad topic was, of course, these tools and techniques in condensed matter physics. So now under that, I have divided it into two parts. The first part, which we'll be doing today, is essentially an overview of condensed matter physics, talking about, I mean, looking at different excitements in condensed matter physics, different problems that people look into, and which are keeping people busy and excited. So I just thought of finding sort of a trendy name. So I put the title for this first part is "What's the Matter with Matters?" So essentially, which is, as I have written below, that overview of condensed matter physics, because condensed matter physics is something which deals with matters. So we want to find out what matters for condensed matter. So the question that we'll start with is, what's condensed matter physics anyway? And what I have written here, that it is the study of macroscopic properties of dense assembly of constituent particles, mostly electrons, but there are others, mostly electrons, formed by placing atoms very close together. So that makes matter. And condensed phases of matter is what interests condensed matter physicists. So, and then as a bit of a advertisement, I have written here that okay. So let me see if I can get a pointer here in that.
Can we increase the volume if possible?
Uh, I okay. So. Uh, uh, I am unable to find the pointer, but I think this thing is working. Is it?
Yes, yes.
Yes, sir. Mouse pointer is working. Yes, sir.
Mouse pointer is working, and then okay, so that's good. That's good. Okay, so what I have written here, that more than 40% of physics Nobel Prize in past 40 years and 50% of those in past 10 years had been awarded for works in condensed matter physics. I mean, CMP is condensed matter physics. Actually, I have not included this very recent Nobel Prize, which is for this year in my count. But I don't think the statistics, my numbers will change significantly because of that. I mean, that, as you probably know, it is outside condensed matter physics. But I must say that it is not the fact that so many people are involved and so many Nobel Prizes are there which makes the condensed matter interesting. I mean, so we would rather, I'd like to believe that the excitements in the subjects are such that it can capture such a broad audience in the global research. I mean, and that's the message I would like to present to you, I mean, through this talk. So, okay, so to begin with, let us look at different branches of physics and let us classify them by length scale, because that's one standard way, or one way at least to be able to classify different areas of physics. So, for example, now when I say that by length scale, what we mean is that what is the distance, typical distance between constituent particles. Particles are sort of within quote, one has to understand that appropriately, and I'll mention in a moment. So what is the typical distance between constituent particles in a certain field? So for example, on this scale at the extreme right, I mean, which is the largest length scale, I have put cosmology, which is a scale of 10 power 20 here and 10 power 30 here, 10 power 30 meter. So that's the length scale. So because in cosmology or astrophysics, we deal with particles which are like planets or galaxies even. So they are separated by a distance of that sort, 10 power 30 to even more meter, 10 power 40 meter, 30 meter distances apart. So which is a huge distance. So when the distance scales between the particles which are like galaxies or planets or sun or stuff like that, so that's the length scale. That's the largest length scale. That's the physics we look into at the largest length scale. And then there is condensed matter, but in between there are other things. For example, just on the right of condensed matter, there will be classical statistical mechanics, and we will talk a little bit about that. But the condensed matter physics actually lies at a length scale of 10 power 0 meter, which is like 1 meter, starting from 10 power minus 10 meters. So this is 10 power minus 10. Each of them is like 10 power minus 10 away. So 10 power minus 10, as you know, I mean, so that's like angstrom, or I mean, that's the length scale of that's the atomic. I mean, not even atomic. I mean, it is basically the lattice spacing scale that people talk about. The distance, typical distance between nucleus, which makes the lattice of any matter. So that's the range of length scale where condensed matter physics works. So that's a length scale which we can observe, I mean, in our everyday life, if not by naked eye. I mean, naked eye, you can see this much, or even maybe a little below this. 10 power 0 means 1 meter, but at least with strong microscope of certain kind. I mean, it's not always microscope, but something which has the effect of a microscope. We can see them, observe them, and so on and so forth. And in the left, we can go to the further and further left. At the extreme left, what we have here is what is called a string theory, which is which works at a length scale of 10 power minus 40 meter. So that's extremely small length scale. So the constituent particles in this topic, in this area of physics, are called string, and they are interacting from a distance of that small distances, 10 power minus 40 to maybe 10 power minus 35 or something. I mean, that's a really small length scale. And then in intermediate, there are many other subjects, like there is particle physics, or high energy physics, which will be just to the right of the string theory, and below that there will be probably nuclear physics, and so on and so forth. So basically, depending on the distance between constituent particles which are making up the physics of a particular subject, we classify physics in different ways. That classification can continue even beyond physics. Actually, branches of science can be classified this way. So what I have plotted here is similar picture, like universe I mean, galaxies and so on and so forth. I mean, 10 power 30 or 10 power 26 written here of that order, length scale 10 power 26 meter. So that's galaxies and universe. I mean, it's universe, galaxies will be even larger scale. And this is the quantum foam, it's called Planck scale, that's like close to the string theory limit. And in between there are various things. So there will be, I mean, galaxies are written here, sorry, and then there's atmosphere, planets will be somewhere here, then ocean, trees, etc. Then people, which is 10 power 0 meter. So this is where condensed matter starts and go down somewhat. Grass, cells, DNA. I mean, this is the biology area. Then atoms, which people study. I mean, people study condensed matter even all the way up to atoms. Then quarks, which is part of high energy physics and goes down to other things. So if you look into this, biology operates in this range. I mean, from here to here. So in this range, roughly speaking. Chemistry works here, atoms to something which is smaller than the length scale of human. So that's the region where
I think
chemistry
the
works.
first slide is visible. You are probably talking about the second slide.
Right, right. Oh, so how is that happening?
Sir, you have
yeah,
you just close the sharing option.
close. I close
Yes,
the
sir.
share. No, it is there. It is there written
Stop share.
share.
Say stop share, and at the
Okay.
time of sharing, you have to choose the application that is in the slideshow view.
So share, and
Yes,
then
sir.
I'm.
You have to find that the slideshow view is there, sir.
We,
So
Yes,
is
sir.
it coming?
Sir, make it in slideshow view, sir.
Slideshow view. Where does one do that?
slideshow is on
The
top.
top, sir.
Okay.
Slideshow is
The top file menu home.
Uh-huh.
Insert slide slideshow.
Okay.
Home insert slide slideshow options, sir.
But wait a
on
second.
top.
At the top, sir.
Right. So if I go there, so slide, then go to new slide. No,
Slideshow.
not that.
Slideshow.
Slideshow. No, actually, I am presenting it from my Google slide. I mean, basically from my internet. This thing. I mean, which is there. View is. So does it work? I mean, can you?
Yeah, now
No,
we
it
can
is.
see the second slide. Maybe you have to just select the sides manually. Now we can see the
Okay. So let me try.
Sir, one thing you can do, sir, at the left side, you just cross beside the slide. Slides, there is written slide, and after that you can cross. So at the left side, sir.
Uh, well, so let me try to come out and present straight from the PPT file.
Yeah, that would be better.
That would be better, sir.
Just select the window of the PPT file.
Yeah. So now I have gone there, and I go to slideshow, and then start from current slide. So does it work now? Second slide shows.
Yeah, it's showing second slide.
Okay. So now can it show the first slide?
Sorry?
Or it is still showing the second slide?
It
Yeah,
is
it
showing
is
seconds.
showing the second
Okay.
slide.
So that's not working then. So then,
Yeah, now it
okay.
is showing the first slide.
Okay. So if I go to
Sir, one
slide,
thing you do, sir, when you share screen, so you choose the first option, sir, screen.
wait a second. So
Click on the share screen
share
and just
screen.
click on the first option, screen written.
No. So if I do that, it shows me several options like desktop one, then
Right.
the
Choose only your
The
present.
first option, sir, first option, yes, sir.
not I mean, first option is desktop one.
No. Choose
Yes, sir,
the
yes, sir.
presentation.
Click on it, sir, first option.
Desktop.
Yes, sir, click it.
Desktop will have all different things, right? I mean,
So
that's not.
whatever you do, it will be displayed, sir.
No. So I mean, so that
So
is
yes, sir,
probably.
whatever you do, it will show it, sir.
Uh,
So
Okay.
if there is full screen, it will be view in full screen, no problem. So here you can do anything, sir.
Yeah. So
Yes,
so
yes,
does
yes.
it show
They're
now the
working,
first
sir.
slide
Yes.
Yes, sir, working, sir.
and second slide?
Yes,
Yes.
sir, yes, sir, working,
Okay,
sir.
okay, so good. So yeah, so that's fine then. So yeah, so I was talking here. So I was saying that sorry. So just to confirm me, it is showing the full screen, right?
Hmm. Yes.
Okay,
It's
very good. So what I was telling is that we have this on the rightmost. We have universe and then various things: galaxies, planet, ocean, trees and people, birds, grass, DNA, atoms, quarks. This way we go to smaller and smaller size system and smaller length scale. So what I was saying that even different branches of science can be sort of classified using this length scale business. For example, this biology operates in this regime. I mean, so something like DNA to human being size. Chemistry operates in regime which is very similar to the area of condensed matter physics that I was showing in the first slide. Geology, on the other hand, works at a larger scale, like oceans and so on and so forth. Atmospheric science works in some range. Astronomy works in a very large length scale limit. And here, finally, what we have physics, which works on all length scale. So basically, physics covers phenomena which occurs at all length scale. It is some sort of a propaganda for physics compared to other subject, I guess. But I guess I can't help. I'm a physicist by profession, so it's probably okay. Okay, so the whole point was that is a useful way to connect different disciplines of science. So now, given that there is another way of classifying condensed matter physics, and I am on a third slide. So can somebody just confirm that it is visible? Just wanted to.
yeah, it's visible.
Okay, very good.
Third slide.
So third slide. So which is it describes phenomena at complex length scales. So complex scales in general, which are complex scales are always regions which are accessible to experiments with relativities, because it's the scale which we can see, the thing that I was telling you earlier, the one that we can realize, and that's why there are experiments, and then there is a fantastic synergy between the experiment and theory and whatnot, everything. So now, how does the complexity change? You can see it here, that if we are working with about one or few atoms, like if you are describing hydrogen or helium, just simple atomic physics, we are fine to work with 100 to the power 0. I mean, it's written 100. Basically, it's like one atom or of the order of one, few atoms. So we can do that. Instead, if we go to simple metal like niobium, which has, let's say, 100 to the 1, that means 100 atoms, then we can use behavior of 100 particles in the metal to describe things like superconductivity, which is electron pairing. We'll talk a little bit about that towards the end. Then we can increase the complexity a little more. We can form compound gallium arsenide, which is the sort of the host of heterostructures of various kinds for developing many devices. So that is required, where you will be dealing with of the order of 10 power 4 particles, and then and that will be helpful to understand what are called uh, quantum Hall effect. I mean, I again will mention little bit scarmions and other exotic stuff. I mean, we have to go to much more number, which is 10 power 4 atoms. And so this way complexity increases. Then for heavy fermionic system, I mean, which is alloys, uranium alloys, we have to work with even larger 10 power 6. And then if you want to understand something which is a rather complex area of physics, condensed matter physics, high temperature superconductivity, which is not understood. It's written here, as well as perovskites. I mean, colossal magnetoresistance compounds. I mean, something that Prabhuddha worked on. So there you have to talk about minimum of 10 power 8 number of particles or even more. So as you go from here to here, and that's the arrow which is given here, broad arrow, your complexity increases because your number of particles that you want to describe increases. So with that, something beautiful emerges, what is known as emergent properties. So emergent properties are properties of matter which is there because of the many particle nature of the system. So systems containing many particles exhibit properties which are special to such systems. So this is little bit sounds like a jargon, because of course, I mean, if you want to describe properties, properties must be special to those systems. So what is special about many particle system? So the thing is that these properties are fairly insensitive to the details of the material, but depends on something else. So just to take an example, you can take different sets of same amount of H2O molecules, let's say in two glasses, which are exactly identical in all practical purpose, and practical meaning that the number of molecules and the composition and the interaction between them are exactly same. They're all H2O molecules. Yet, I mean, they follow identical microscopic law. I mean, if you want to consider it as Newton's law, yeah, it's the identical Newton's law which works between those H2O molecules. Or if you want to talk about quantum mechanics, is I mean, so sort of equivalent status is of the Schrodinger equation. That equation will also be the same between the two. Yet one of them could be ice, other could be water. The fact that you have two physically different states, ice or water, is actually the fact that they can exist that way is an emergent property, and that property arises just because you have a system of many particles. So you can think of it like if you take one H2O molecule, and if you thought that that was water, it's not clear whether that one molecule of H2O will give you a sense of wetness. I mean, basically the fact that it's weight. So there is no such thing associated with one molecule. So you require many particles, many molecules of H2O, which are coherent, which is acting coherently collectively to give you certain properties like the wet feeling of a water. So such properties are called emergent properties. So emergent properties are important to then classify what are called different phases of matter. So for example, ice and water are two different phases of H2O molecule. I mean, assembly or collection of H2O molecules, right? So condensed matter physics, now I'm in a better shape to define condensed matter physics in a more quantitative manner, that it is something which deals with the understanding of different phases of matter, which are like ice and water, and the transition between these phases. So broadly speaking, this is what condensed matter does always. So it studies the phases of matter to understand each of the different phases that might be there with the material, and also how does one transit from one phase to another. For example, melting of ice into water upon heating is a phase transition. So that's what are called phase transitions. Now, broadly speaking, condensed matter physics is divided into two broad parts. One is called a soft condensed matter. It's a very funny name, however, it's a very popular name, and hard condensed matter. So, soft condensed matter is essentially the area of condensed matter which is whose richness is contributed by classical physics, meaning quantum physics is not so important. So here you will be talking about membrane or polymer or things like that. I mean, mostly developing on the technology developed within what is called classical statistical mechanics, and application of that for various physical physical as well as important technological problems as well. I mean, polymers and all has many different aspects, and elasticity. I mean, you study all of that within soft condensed matter. So basically, the richness of the problem that you study is contributed by classical physics, thermal physics, you can also say it that way. Instead, the hard condensed matter, it's not really very hard to work in this condensed matter. It's just the opposite of soft. So there's not too much meaning that one would like to associate it with hard versus soft. But here the idea is the quantum physics instead of classical physics leads the surprising and new outcomes from this particular area of condensed matter. Okay, so this is the way, I mean, you want to classify, and then there are many different phases that people deal with in condensed matter. I mean, phases can be classified from various different background. So for example, you can classify like solid is a phase versus liquid. Then you can talk about metal versus insulated, depending on the electrical current carrying capacity. You will differentiate between two phases. Then there are magnetic properties. So there, based on that, you can have paramagnet, you can have ferromagnet. Paramagnet is something which is essentially something which is not magnetic. I mean, they're magnetic atoms. I mean, basically magnetic spins, but they're not really oriented in a particular manner. Then ferromagnet, where everything is what are called spins or magnetic moment. Yeah, so maybe that is a better thing to say. Magnetic moments are all aligned parallel to each other. Antiferromagnet is a phase where these magnetic moments are anti-parallel to each other and they cancel. I mean they're anti-parallel, but the size of each of the magnetic moment is same. So when they're anti-parallel, they cancel the effect of each other. And then there are ferrimagnets, which are like antiferromagnet. However, they don't cancel completely. Yeah, and then you can have dielectrics, which are some kind of electrical insulator only. However, they have polarizability. I mean, there is some energy storing capacity because of their polarization, electrical polarization. So those are dielectric. Then you can have superfluid. So now this is very uh, common. I mean, to call super, I mean, it's sort of being little unimaginative with names, I think. So anything, if this is a fluid, and if the fluid nature is something superb, then you call that superfluid. Essentially, that's it. So superconductor is a conductor which is superb conductor, in the sense that I mean, it conducts everything. There is no resistance at all. It conducts everything that comes in. So that way, there is something else which are called super solid that people are very excited. People have been very excited about, though it's not found yet. So that is super in the sense that this is not a solid which is superbly solid. It is funny because it is not. So super solid is an object which is at the same time which is a solid, and it is also a fluid. So it is a super fluid which also shows solid properties. I mean, this is very strange concept, but and I said that they are not found, but people believe that they can exist. At least there is nothing scientific which prohibits them for a phase to exist, which is like a super fluid, however solid at the same time. So there are many exciting phases that one would like to see, and people studied them in the past, and people still study them because they are expected to be found in nature. So we saw most of them, except for super solid in this case, and we hope that we'll be able to see them in nature if we study and thereby quantify them, qualify them better and better. So now, if I want to come to the particular one, like a melting transition, so on this left side, what I have is a solid. So solid has a underlying lattice. Lattice is a skeleton, which is like this cage that you are seeing because of the straight lines passing through each other. And at the vertex is where two orthogonal or perpendicular lines of the skeleton cross each other, and that's where the constituent particles live in a solid. So solid of gold will be gold atoms will sit at this point, so in the vertices. On the other hand, if you're looking into liquid, they are not arranged in such a regular manner. So here, because it's like a cage, and then on the vertices of a cage, the particles leave. Here it is not. Here everything is sort of jumbled up without any regularity. So which is represented here, solid to liquid, and then there'll be a transition. If you increase the temperature, and actually if you increase the temperature, you can go from solid to liquid to even a gaseous phase. So that's something which is common, and we all must have seen this. Similar phase transition occurs in magnet. So here is this horseshoe magnet, which has a north pole and south pole, and it is made up of small little things which are called magnetic moments. So in a paramagnet, these magnetic moments are not aligned. So we know that these magnetic moments are such that the opposite poles attract, meaning there are one pole which is north and another south. So each magnetic moment looks like this. So now in this ferromagnetic orientation, they are arranged because each of these magnetic moment is one after another, such that the north pole is connected to south pole. So that thing is broken in a paramagnet where everything is random, the orientation is random. So you again, by increasing temperature, you undergo a transition from a paramagnet at high temperature and a ferromagnet at low temperature. So now you define something called order parameter for studying phases, which are like the propensity of having this kind of a nice ordered manner. I mean, so the fact that these are arranged in a nicely ordered manner is what quantifies that is called an order parameter. And that, as you increase temperature, of course, has to disappear. So this is a plot of order parameter. Order parameter has some finite large value. With increasing temperature, it comes down. It remains, though, ferromagnetic all the way up to this point, and beyond this point it becomes paramagnetic. I mean, because they become random, so there is no order anymore. And that temperature is called a Curie temperature for a ferromagnet to paramagnet phase transition. So this is called ferromagnet, and the other one is paramagnet. So these are different phase transitions I'm telling you about. What is very exciting and interesting is that in condensed matter, I said that people also study large systems. So you study what are called a traffic jam model. So people try to develop some kind of an understanding for the physics of traffic jam, so that one develops some kind of a predictability. So there also you see the traffic jam model is such that you have, when you have ordered traffic, there is no traffic jam. They are very nicely ordered pattern of vehicles on road. Typically, these are seen in foreign countries. In India, what you have is some very irregular structure on the road of traffic on the road. Well, not always, of course. We have very ordered traffic other places also. So, but the chaotic traffic is the onset of a traffic jam. So, I mean, because these cars are buses, they have finite structure. They are not compressible. You cannot compress them, so they get stuck, and when they can't move, and so there is a phase transition in that also. So even that is studied, and that is studied within the premises of soft condensed matter or things like that. So people study other interesting things also, which are like self-organized criticality, sand pile model. So what people study is that you must have played this game by seashore at your younger age. So what you do is that if you drop sands and pile them up, they slowly grow grow in height, and they make a conical structure like this. Addition of sand grain, the slope increases, but then it reaches a critical slope beyond which, if you put sands, the additional sands just there is an avalanche, and that the slope decreases. I mean, basically, there is a point where the system, which is a sand pile here, moves towards the criticality, in the sense that that's something which is critical, up to which it takes sands, and beyond which it does not take sands, and that happens without any. So, like in other examples also, from ferromagnet to paramagnet, we see that it was a ordering that was there, and ordering goes away beyond some temperature, and it goes to a paramagnet. So similarly here, it goes from some situation to some other, and there is a criticality, in the sense that only the exciting thing is that this criticality occurs without any external tuning parameter. There is no temperature; it's just dropping sand, and that has to do with that kind of concepts are related to various things like the river network. I mean, so basically, so that is a self-organized situation, right? In nature, river networks is created just by themselves, by various interaction between various things, and the details we don't have to know, but I mean, there is a self-organized criticality in river network also. Now, many of these phase transitions that we are talking about, so what is very exciting about physics in general, and also condensed matter physics, that symmetry plays a very important role. Symmetry is always beautiful. So like here, the symmetry is that if you have this butterfly, if you reflect this butterfly across this axis, vertical line here, which is the axis of reflection, then this side falls on top of each other exactly. So that's the symmetry, that you perform some operation by which it remains invariant. I mean, whatever is on this side will fall on top of this side exactly. So that's the symmetry, and symmetry has a very important role in physics. So this is another symmetry, which is reflection of Taj Mahal on Yamuna. except for this is not an exact symmetry, right? Because you can make out that this is water and this is the real thing. So the point is that symmetry plays a very important role. They're intimately connected to phase transition. So what is believed, or what is actually what is shown almost in every almost I'll explain later, in every phase transition, that a phase transition occur when the symmetry changes. Like you go from solid to liquid, you change the symmetry, and it is believed that you go by going from solid to a liquid by increasing temperature, you go from a lower symmetry state to a higher symmetry state. So why lower and higher, we don't have to worry right now, but it can be understood, and that's what it is studied in physics regularly. But what is very important is that the change of symmetry is related to a phase transition. And other important aspect is the profound concepts which connects various things. So, like for example, there is some concept of universality associated with a phase transition. So there is a, so all the examples that I have taken so far, you can see that there is an ordered disordered transition. So there is an ordered phase, be it in solid or in traffic, regular traffic, to a disordered phase, be it liquid or a chaotic traffic. I mean, so there is a universality of concept of which relates different phase transitions. So now what people do, I mean, what is also a very important job of condensed matter physicists is the notion of phase diagram. So people try to construct phase diagram. So phase diagram is something which is simple. So it is, as we said, that by increasing temperature you go from solid to liquid to gas. So for as a function of various tuning parameter by which you can access this transition, you want to map out the regime where a particular phase exists. So like for example, as a function of temperature and pressure, this is the regime of solid behavior, this is the liquid behavior, and this is the gaseous behavior. In fact, liquid and gas beyond this point, which are called critical points, they are not different. I mean, you can go from one to other smoothly. What is smoothly, what I mean by smoothly is not something that I'll explain now, but don't worry. So what the point is that if you, let's say you remain at a particular pressure, which is, let's say, 1 atmospheric pressure somewhere here, and then you increase temperature. So this phase diagram will tell you how much temperature is going up in the horizontal direction, how much temperature you need to increase, by which you go from solid to liquid here, and then you go from liquid to gas, and so on and so forth. So that's the role of phase diagram. So it's like a map. I mean, just the way you have maps of the world with different colors, and these colors don't exist. I mean, I have colored it by hand. I mean, because phases, by the definition of phases, they don't come with color. Just the way in map, the continents don't come with color, but you are marking your territory. So when you are describing your phase, you are marking your territory just the way in the real map of the world, you are marking your territory by calling this region North America, and thereby making sure that the North Americans live there only, and so on and so forth. So it's sort of the same idea. You have very interesting phase diagrams. So there is a phases that you classify this way, and the transition you classify by going through the boundary of phases. So if you can understand for a material the phase diagram, I mean, you construct the phase diagram by doing experiments, and then by doing more experiments, and then some kind of a theoretical input. If you can develop the understanding for phase diagram, then you are good. I mean, that's the job of condensed matter physics for a particular material, and condensed matter physics does that for all sorts of matter, all sorts of materials, and that's the exciting part of condensed matter. But this is what the traditional condensed matter had been, which is that you have natural phases which occurs in nature. You try to understand that. While that is very exciting and people do study those areas of condensed matter, I mean, things have moved in an interesting direction in recent times. So for example, started with the question, which is what I have written here on the top. So what I said, that phase transitions are always present with symmetry breaking. So there was a symmetry, and the symmetry will change at a phase transition. This is not always the case, and the Nobel Prize of 2016 was awarded for finding for the first time, or comprehending for the first time transitions which occurs though it is not associated with a symmetry breaking, and that turns out to be very exciting. I mean, so they are called topological phase transition. I mean, this particular one is called topological phase transition. By topological phase transition, what one means is that there are some objects called topological defects. So, for example, these are called vortices. Vortex is some name that probably gives you some impression. So it's like a swirling amount of water in this case, or cloud, or whatever. I mean, you see it is rotating around some center. So and that makes it like a that is one of the topological defect. It's called vortex. I mean, vortex is something that we all see probably first thing, well, in the morning when you flush your toilet seat, the water actually moves in a manner which is like a vortex, and tornado and all sorts of things that we know. So you see, this is what I meant by making a vortex. So this is like water, and then there's swirling water which is making something like a, which is suctioned out from below, and then this is I mean, so it makes like a shape of a conical flux, right? I mean, so this is like a cone. So this thing is going down, and this swirling thing on the top. So this is the top view, and this is the side view. So that is called vortex. So what is the role of the vortex? So it turns out that unlike ordered disordered transition, there are some transitions that occurs because this I mean, this kind of a topological defect like a vortex, and there is something which is opposite, which is anti-vortex, I mean, which is here. So vortex is when there is arrow which is like a field, like the velocity, you can think of it here. So this field is circulating in some manner, and in the some manner meaning, if you are going like this along the, let's say, clockwise direction, the circulation of arrow is along that clockwise direction. On the other hand, the direction of arrow. On the other hand, if you're going in the clockwise direction, the arrow is trying to move out from the direction of circulation, right? I mean, you're going like this, and this arrow is trying to go like that, and always is like that. So such objects, such imperfection, that the imperfection in the sense that ideally for a very regular thing you would expect all arrows to point in the same direction, like what it is doing here. So it changes dramatically by doing this way, and you can show that if you have this kind of swirl, I mean, in these two opposite direction, and they're confined in a small region, then all these randomized direction of arrows are limited to a small space. On the other hand, you might have a situation when these two things move apart from each other. So these are called topological defect, like vortices and anti-vortex, vortex and anti-vortex. So you can have a phase transition by separating out in space, or it's the formal way of saying this is unbinding this topological defect. So when they're tightly bound, there is not much disturbances away from their region. However, if they're very far from each other, the two are very far from each other, there is a lot of disturbances that will cause, and it will go to a different phase. So there is a very different conceptual way of classifying phase transition because of this new object, and it was first time discussed by Kostelis and Thouless, and then the ideas were advanced by Duncan Haldane, and they got the Nobel Prize in 2016 for that. I mean, to understand phase transition beyond the standard paradigm of ordered disordered transition. So topology is a subject of mathematics. So by the way, so how am I doing with time? Can
Yeah,
can
you
some
have about half an hour to
half?
45 minutes. Yeah,
Okay, so I'm good. Thank you.
half an hour. Yeah,
Okay, half an hour. Very good. So what I'm writing here is the topological system. I mean, because of the top thing, I can't see what is written there. Topology is certainly something that I have had here. So topology, I mean, so what I said is the previous slide is that there are topological defects which drive which can drive phase transition also. So what is topology? Because topology is something, a direction where condensed matter physics is marching with a rather high speed. So topology is something which is called which is a part of mathematics, which deals with geometry or the shape of object, right? But it is not geometry in the sense of it tries to differentiate between a square and a triangle, or a isosceles triangle and differentiate between isosceles triangle with a right angle triangle to equilateral triangle. I mean, those details are not the part of topology. You can think of it as a part of geometry, study of geometry with object which are elastic. I mean, which are like rubber sheet or something which can be deformed easily. So this is, and from the topology point of view, what is very exciting is that the I mean, in the description of topology, what really matters is the number of holes that a object will have. So in that sense, in topology, to a topologist, a donut shape, which is like this, or you can think of it like a tube or something, and a coffee mug, coffee cup here, they're actually invariant topologically. They're the same thing to the eye of a topologist, because remember I said it is like an elastic object, like a rubber sheet or something. So as a result, you can deform one gradually, slowly and gradually, to give the shape of the other, which is a cup in this case, starting from here. And this is what is being shown here as a movie, that you can continuously and gradually deform a donut to make it into a coffee cup. So what is crucial is that it doesn't matter what is the shape of the connected object, but there was one hole which is respected till the very end. So that object, like a hole, its genus, I mean, that's called the topological invariant. I mean, the number of holes. So topologically, while these two are equivalent, however, what is not is a shape like that, which has three holes in this case. So I mean, so if you take a cup or a donut without punching additional hole, you cannot go to this shape, which is actually called a pretzels. I mean, it's some kind of a snacks. I mean, which is not so common in India, but nevertheless, it is there. So topology studies that, and you might say that that okay, so fine, so why is that important? For example, let's say in condensed matter physics, because condensed matter physics describes object by quantum mechanics at a very small length scale, and it has apparently no relation to how many holes you have, or nothing to do with a donut or a coffee cup, not even a pretzels, right? However, this is what this people, Costelis, Howless, and Duncan Haldane showed, that even microscopic matter at the smallest length scale can show macroscopic properties which are topological. So that's the main point of the connection of topology to condensed matter. And then that has been found in various situations. So for example, this is the vortex that I was showing you earlier. A topological defect will be something like this, which is, let's say we are talking about lattice of a solid. So suppose you have one lattice line, I mean line of atoms, which suddenly stopped. So that's a defect, right? I mean, that can happen. I mean, that is natural, that any material that you have naturally comes with defect. Either it is inherently there, or because of some operation it has been created. So defects are very natural. And then whenever you have these topological defects coming up in a material some way or the other, and another particular statement will be, and this I am expecting you to sort of know, that a property of a material is strongly dependent on the lowest energy state that it can have. I mean, that is called a ground state energy. So the point is that if your ground state somehow, ground state of a system, the lowest energy state, and that's why that has the largest probability of having found. I mean, get without requiring any energy from outside. I mean, or at least with very little energy from outside, if you can access this kind of defects, they can play a very important role in defining the phases as well as the phase transition. And when you have this topological object which are doing that job, topology starts playing a very important role. So there are many examples of topological defects. So like you can look at your own thumb, you will have lines running like that, and then suddenly one will stop like that. So this is called a terminal point topological defect. So they are very common. I mean, they're used in polymers. So if you are describing polymers in classical statistical mechanics or soft condensed matter physics, I mean, there you will encounter this kind of a topological defect. You find that in your own hand. I mean, they're always there. So there are values to sort of trying to classify properties with respect to topology and topological defects, uh, which makes it very exciting, and they occur elsewhere also. So for example, I mean, I'll try to give you a glimpse of what is exciting about them quickly. So there is something called quantum Hall effect. I mean, you might not have heard the name not all of you might have heard the name quantum Hall effect, but there is a classical version which is probably known to you. So Hall effect is an effect in which if you pass current through a material and you put that material in a magnetic field which is like this direction B, which is shown here, which is perpendicular to the direction of current, then then the electrons which are moving on this metallic plate, moving from this side to that side because of current, driving current, they get deflected because of what is called a Lorentz force, and they try to accumulate. I mean, the electrical charges accumulate on one side. Depending on one side, it accumulates to the other side will have the opposite charge. So effectively, you can develop some kind of potential drop across this transverse direction. I mean, the direction which is transverse to both electric field as well as magnetic. So that is called a Hall voltage. And so what happens for quantum Hall effect is something which occurs when the magnetic field is very strong. Also, you need a two-dimensional surface, so it will be as perfect as possible, a two-dimensional substrate, two-dimensional plate. Then what happens is that the resistance, I mean, which are called the transverse resistance, because so field is created in this yeah, because of voltage drop, a field will be created here and the current is passing in this direction. So the transverse resistance that will be generated, those become quantized. Like this is the regime of I mean, this is as a function of magnetic field, so that's the Hall resistance, it's called. So that goes typically with magnetic field linearly. That's the regime of Ohm's law. So beyond that, when field become very strong, they become quantized, meaning they only occur at a certain values as a plateau. I mean, so there will be a range of magnetic field where it is constant, and then it will jump up to the next value and so on and so forth. So that's quantum Hall effect, and that has many different aspects. People actually there are two Nobel Prizes which went into understanding the quantum Hall effect, and that's really fantastic. People understood very well. It is only relatively recently, I mean, not well, it started some time back, but recently people started understanding that this quantum Hall effect is actually very intimately connected to topology. So just the way I said that there are topological invariant, and then in this case it is genus, the number of poles. So there are always some topological invariants. So there you can classify quantum Hall effect in terms of topology, and they're called Chern numbers, which are topological invariant for quantum Hall effect. And I don't want to go to the details of that, but just to tell you little bit more, I mean, just a little bit more, is that because you put a very strong magnetic field, so what happens is that what happens is that the electrons, as I said, will get deflected because of the magnetic field and then transverse magnetic field and current placed in a crossed manner, transverse manner. So then they, because they will get deflected, they will start, I mean, if the magnetic field is very strong, they will start circulating in a small orbit like this, the one that is shown here, inside the material. So as a result, electrons won't transport at all. They will just keep circulating in this region. So they become localized in a small a region of space of the material and just stay there. They don't contribute to current conduction at all. So it will appear that the system is like insulating. On the other hand, you can imagine what will happen to the electron which is near the boundary, because they're near the boundary. So this will come and hit the, I mean, because of the boundary, this circuit will not complete. It will come hit here, it will hop back, and then it will go like this. So it cannot penetrate because it's the boundary. So electron starts moving around by skipping orbit along the boundary of the sample, right? So it's a very nice or fun, exciting situation in which the bulk of the material does not contribute to current conduction. However, the surface does, and that is something which has a very strong topological properties. And these are actually excuse me, these are actually called topological insulator. The one that I just described, the interior does not conduct, whereas the surface or the boundary conducts. I mean, that's the property of a topological insulator. It's insulated because of topology, and they are very exciting for two reasons. If that can be achieved, one is that because the current goes only in one direction, it has very little degradation, because but current is responsible only from a very limited region of space. So if you have, let's say, put more disorder, and disorder is something which you put randomly, I mean, because you can control disorder. That's why they're called disorder. Some impurity. By disorder, I mean, if you put some impurity, they will likely go in the bulk of the sample, and they will have hardly any effect of that current on that current. And also the current being in one direction and it's not colliding with anything, so that current is very robust. I mean, the magnitude of current. Also, if you change the shape of the material, there is hardly anything which changes the nature of the current flow. I mean, the area will increase, the distance, the perimeter will change, that will happen, but the amount of current that will flow is not going to change much. So you can have very robust conduction properties with this single channel of this skipping orbit motion of electron. So that makes, and that has a very strong topological property in some sense, that so just the way you in the previous example, so it's the number of holes that determines it, right? So if you think of a geometry like that, and if you want to talk about, and this current, by the way, this is the electronic state which leaves like this, are called edge state, because it leaves on the edge of the material. So the number of edge that you can have will determine the current carrying transport properties, and that will certainly be dictated by the number of holes like you have. I mean, so there'll be one edge inside because of inside hole, and one edge outside in a geometry like this. So the topological invariants are going to determine the transport properties in a significant way, and that makes it very exciting. Uh, was there a question? Sorry?
Wrong number.
Oh, okay.
Yes,
Okay.
no, sir. Please
Very
continue,
sorry.
sir.
Okay. So the thing is, so what happens is that, so what I have described in terms of quantum Hall effect is something very interesting, but in actual topological insulator, the cyclotron motion or orbits of electron does not occur because of magnetic field, but for something else. Much of the topological effects originate from what are called spin orbit coupling. I mean, so that's some property which is more details, and I won't go into that. So I mean, there is something else. I mean, the internal property, like here, the magnetic field is an external property. So you have an internal property which is spin orbit coupling that plays the role of the magnetic field, and that's what makes topological insulator behave the way topological insulators are. But even in quantum Hall effect, I mean, because of magnetic field, you will have interesting physics, and then this, I mean, quantum Hall effect has other Hall effects, anomalous Hall effect, spin Hall effect, and all that. I mean, spin Hall effect is one where you don't have the charge carrier like the one that I have just described because of magnetic field and so on. So charge meaning electrons move around. Here in this case, it's not electronic charge which moves around. What moves around is electronic spin. So it's like spin is just transporting. I mean, there's only one variety of spin up, let's say, I mean, which is moving in one direction, and spin down is moving in other direction. So that edge state will carry current, and that will lead to what are called spin Hall effect, which is very similar to quantum Hall effect, but for spin, not for charge. And so the transport properties of material is at the forefront of any technological advances for devices, etc., etc. And spintronics is a branch which is very popular. I mean, which is changing the transport from electronics to spintronics. Electronics is the one where the transport of electrical charge is carried by the electron, whereas in spintronics the transport is affected by spins. So by studying this topological property and thus understanding the spin Hall effect, we believe to contribute significantly to our understanding of technology and devices. So that's something which is exciting. Now let me come to yet another exotic concept, just like topology, which is now become has now become an important part of condensed matter physics. Another thing is called entanglement. So these are like deep questions people used to think of quantum mechanics. I mean, when I was a young student, I mean, I was doing my masters or even PhD, uh, there used to be a different area of physics which used to be called, I mean, which might still exist, and there are fantastic people working in those areas, called foundations of quantum mechanics. So foundations of quantum mechanics at that time was believed to be areas which is little far from reality. So in present condensed matter, the foundation of quantum mechanics has actually taken the center stage and became very important, and generating a lot of interest, which are experimental, to observe and apply applied physics part. So for example, this is one. So entanglement is the extent of quantum correlation, the quantumness, if there was an English word like that, between different parts of a system, leading to, I'm so sorry for this spelling mistake, observable properties. It should be leading to observable properties. Okay, so that's quantum correlation is called entanglement. But before describing that, let us understand quantum superposition, and that's something which had been there for a long time. So if you and it is called interference, I mean, which leads to interference. So you can think of a geometry like that, that their electron is coming through some pipe like this, and then split into a circular ring.
Hello?
Yeah.
Hello? Yes,
Yes.
sir. Can you see the question, sir? One question is coming from Uttam Kumar Basar.
I can't see the question. I mean, I have to then go
Question is
out.
that you mentioned that only classical physics is relevant to the soft condensed matter. In our quantum theory, not quite developed yet to apply, it is to the
Uh,
soft condensed matter. On the soft condensed matter system is such that quantum effects are negligible.
Yeah, in soft condensed matter, I mean, quantum effects might be there. I mean, in the system. However, typically we'd like to understand the phenomenology, like a phase transition. Let's say is a phenomenology. I mean, it changes from one phase to other. So such phenomena in soft condensed matter are not due to, let's say, the quantum mechanics. Quantum mechanics is not that strongly involved. I mean, you can always take the system, soft condensed matter system, to a quantum limit where quantum mechanics will be important. But the interesting physics, let's say, I mean, I just take a very quick example, like the traffic jam model that I was telling you, or a very common other example is a very similar example is the glasses. I mean, window glasses. So glasses is people believe that it is like a phase. I mean, glass is not really phase. I mean, the window glass that we all encounter all the time, that's neither a solid nor a liquid. It is somewhere in between, but it is not a different phase. But people try to understand what is responsible for their existence. The glasses, super cooled liquid is what they're called, broadly speaking. I mean, glasses are a super cooled liquid. Yeah, that's the terminology. So the fact that that window glass behaves like a glass, or sorry.
Sorry. Question answers will be after 5-10 minutes. Just finish. Let him finish the talk. Right.
Okay, okay. So but yeah, just one sentence on that, so whatever interesting property of the glass, be it window glass or supercooled liquid, which it exhibits, are not due to quantum effect. Those are classical effects. So that's what I meant essentially. Okay, so I came out of the presentation mode. Can you see my slide? I mean, my window.
Yes, yes.
Okay, so I'm on the entanglement. Yeah. So what I
But
said is that
you have 5 minutes.
5 minutes. Okay, so I will wrap up quickly. So if you have electrons which can split up, and because electron is not really particle, as you might have heard in quantum mechanics, it can also behave like a wave. So it can split up into two and again recombine. And when they recombine, so that's the superposition, and that recombination, they hit hard against each other, and that produce what are called interference, and something that we learned from the very basic physics. Waves interfere, so it's just that interference. So they really exist. I mean, that's the superposition. So superposition is something what is jokingly discussed in Schrodinger cat, but I don't have time to get into that story. But one very important aspect which is technologically relevant for superposition is what is called a qubit. So in computer language, everything is stored, every information is stored in a bit, which is classical, meaning it is either zero or it is one. Now, in quantum physics, because one can live in a superposed state of matter, one can have something. So, if in classical bit is represented yellow by zero and blue by, one by blue, then in quantum bit can exhibit which is bluish yellow or yellowish blue, which is a quantum superposition of both of these two numbers, and that's called qubit. All right. So that is about superposition. So what is entanglement is something which is very exciting. So what is said that you have, let's say you have two objects which are classical. One is red ball and blue ball, which are not interacting. They're very far from each other, and you bring them very close to each other such that they interact. And once they interact, they get entangled, meaning they get connected to each other. So entanglement is property by which two particles gets intertwined, as if they're intertwined even if they're separated. Talk about that, but they get intertwined like a small cartoon that I have here, or they get intertwined just like the braiding of this very beautiful braiding of this girl, which is shown here. They get intertwined. So that get intertwined by some interaction, and once that happens, this becomes the balls become either bluish red or reddish blue, whichever you call. Both of them become like that. The point is, what is entanglement is that once that is done, if you now make them separate, take them very far from each other, they remain like that. I mean, if just making them go very far from each other doesn't make them blue and red anymore. So this is what Einstein described as, I mean, when this was first envisaged, I mean, it was called a spooky action at a distance. The point is, even now, when they are taken very, very far, they are still entangled. Entanglement won't go away. So they will be bluish red or something. I mean, in this picture in the movie that you have, I mean, so you'll see this when it is blinking, that's like bluish red, that thing. However, if you measure one, you will find one is blue. I mean, you will find either blue or red, any one of them. So once you measured one, you know that it is blue. Immediately, you know the other one is red. So remember, you have taken them far from each other. So you have actually taken the two at the two end of universe. There is no way they can communicate a signal instantaneously from one to the other. Yet, because of this nature of quantum concept of quantum entanglement, once you know one color, you know the other. I mean, so that's what is surprising. So that's a very deep quantum concept, and it turns out that they are expected to have applications to quantum computation, cryptography, teleportation, and all that. So all these concepts, which are highly theoretical and philosophical nature, has become part of condensed matter physics and enriched the subject in recent times. So with that, I come to the end of this part, and there are basically what we have been discussing, various interacting many particle system. I seem to have lost my, oh, no, I have it. Many particle system. So they are described in many different poetic languages by champions of people who practice them. Philip Anderson described them as, accepting them as more is different. More things you have, more difference you will find, that the coherence between that different is what drives the field. It's an incomplete revolution in language of Pierce Coleman. So what are very important is that condensed matter physics link material science, chemistry, and engineering. And recently it has developed overlaps with biology, biotechnology, medicine, and various other things. It is responsible for majority of technology developments, and it's a very large field. I mean, again, this is not just for boasting as a condensed matter physicist, but it is the largest subdivision of physics. If you look at the American scene, one third of member of American Physical Society belong to the division of condensed matter physics. DCMP is it is called. So it is all ours to explore various excitements over this broad range that I have described. So this is one part. Now I probably have exhausted my time, right?
I
Prabhupada?
can give you another 5 minutes, but just 5 minutes.
Okay, so maybe I just take 5 minutes, because I thought, I mean, so this is the broad introduction I wanted to discuss, and then I wanted to develop some techniques in the next lecture with connection to some phenomenology. So I just wanted to quickly introduce some I'll just speak for 1 minute or two, maybe not even five, to tell you to sort of give a teaser for what is coming in the next lecture. Is that I will talk about, I mean, one of the things that I will be talking about is called disordered superconductors. It is the area where I worked probably for the longest of the time in my research career. So superconductors, you all might have heard about. I mean, so this is some superbly conductor. I mean, it is a lossless conduction. I mean, there is no resistance of the material. The resistance of the material will fall to zero. Like if you look into this, so this is an experiment of measuring the resistivity of bismuth, which is written here, bismuth. So it is called a normal state. So resistance as you go down, at least if you are at a very low temperature, remains almost constant. It will actually decrease a bit. At high temperature, the resistance increases, but we are not in that range. We are at a very low temperature, like 5 Kelvin or so. So it comes down and drops directly to zero, and that's the signature of a superconductor, that the resistance go to entirely zero. So people have put enough effort to understand that. So that's what is shown here in this, that this is the temperature axis, and this is some other axis, which is like the order parameter. You can think various superconducting correlations, superfluid density, which is actually a measure of superfluidity, or energy gap, which is the order, which is also the order parameter. So order parameter, remember, as a function of temperature, will decrease and go to a disordered phase, which is metal in this case, and low temperature phase is superconductor. So the way superconductivity comes into being is that it is found that it is described very well by BCS theory, which has very important ingredients, which says that electrons, while repel each other normally, but in superconductivity they attract. So that's a very strange thing. That's very uncommon. The way it happens is shown as a cartoon here. That what happens, I mean, I have to start from a particular time because of this is a movie which just keeps repeating. So initially at high temperature, all the atoms are doing like this jiggling, and this red is the electron. So you take the temperature to a very low value, then every this thing freezes, and when electron moves, then as you see that nearby positive charges which are blue are getting attracted to this. So now the next picture is given here. When the electron moves and these positive charges get attracted to it, then a second electron gets attracted to the first electron, because it is actually getting attracted to the positive charges which accumulate close to that electron. So as a result, there is an effective attraction which is created, and you go into a superconductor. So superconductor is described by an order parameter, something that I have earlier described, and that order parameter is given as delta, which in this case is a complex number. It has an amplitude and a phase. And in pure superconductor, which is spatially homogeneous, and this is where BCS theory works. I mean, in absence of disorder. So what is found quite excitingly, that if you increase disorder in the sample, and by increasing disorder you go up in this direction, so each trace is for one higher disorder. So it turns out the superconductor, the transition temperature where the resistivity drops to zero is marches down to a smaller and smaller value, and beyond which it does not behave like a superconductor, it behaves like an insulator. So in presence of disorder, how to describe superconductor is the whole broad area of disordered superconductivity. And there is extensive research has been done. And I have kept the result as a function of disorder, how these different things will behave. So what we'll do, we develop something called inhomogeneous mean field theory in next lecture, where we will try to develop the technology by which we can understand, do the calculation to understand behavior of disordered superconductor. There are a lot of work which has gone into it. I mean, by us and others. I have listed some of the works that I was involved in uh, which concluded some important points about this thing, and which will be, so we'll develop the technology or techniques for doing that in the next lecture, as well as some other technique with Monte Carlo. So that's the teaser for the next day, and I will stop here. Thank you for your attention, and I'll be happy to take questions now.
Right. So we thank Professor Amit Ghoshal for a very inspiring and lecture, and covering a very broad perspective about condensed matter physics. So now the session is open for questions. Any questions? So I think there are some question and answers and some chats also which have come. So Mr. Uttam Kumar Basak has a question.
So how do you see the question?
Just
Kumar Basak, you can unmute your mic and you can ask the question. Sir, at the bottom you can find the mute, unmute,
Chat.
and after that question answer. Yes.
Oh, question answer. Huh? Okay. Yeah,
Kumar Basak, sir, you can ask your question by unmuting yourself. Uttam Kumar Basak, sir, please unmute your mic at your end. Yes, please. Please ask, sir.
Hello, sir. Can you hear me?
Yeah, I can. Please go ahead.
Sir, my question is that you mentioned that only classical physics is relevant to the soft condensed matter. So my question is quantum theory is not yet developed to apply it to the soft condensed matter, or the soft condensed matter system such that the quantum effects are negligible?
Right. So what I was trying to answer, I mean, when this thing came up during the talk, is that soft condensed matter is very interesting area, and I mean, the material which are under soft condensed matter, if you take them to very low temperature, quantum effects will be there, and quantum effects will be important. The point is, when we say soft condensed matter, we try to understand certain properties of soft condensed matter. So soft condensed matter is, so this is what I was telling. Let's say the glasses. I was taking the example of glasses. So, window glass, right? So the transparent material, the glass, glass bottle and all that, right? So this glass bottle the glass is actually a very interesting phase of matter. It's actually called a dynamical phase. So it's not even a phase, because whenever we talk about a phase, we mean equilibrium phase. So something is in equilibrium. It's a dynamical phase. It's non-equilibrium. Okay. So coming to the main point, that glass is something which has a property which is shared between uh, liquid and a solid. So in some respect, it is like a solid. It has the rigidity like a solid. However, it has symmetry that of a liquid. So now, because of certain unusual features, glasses are very important and they are studied. So now, whatever is unusual about glasses, it is believed, and it is more or less found true, that it is the classical physics which dictates dictates or which determines the unusual or exciting properties of this material. So in that sense, it's classical. So it doesn't mean that the constituent matter of glasses are always cannot be quantum. So there are small particles. At a length scale, they will behave quantum mechanically, but it is the collective behavior of glasses which are of interest, or polymer for that matter, which are of excitement or interest. Which makes them useful for industry or anything. So something that people would like to know are governed by classical physics. So that's, in that sense, soft condensed matter. I meant that the richness is provided by the classical physics. Does
Okay,
that
sir.
does that answer your question?
Yes, sir. Yes, sir. Okay. So
Okay.
thank you, sir.
Thank you.
Okay, I have one question, which
Ah.
is I got a little confused when you were talking about this quantum Hall effect, and
Mhm.
you were showing these cyclotron orbits, and there was this creeping electron along the
Sleeping
edges.
electrons. Yeah, yeah.
Yeah,
Right, right.
yes,
Mhm.
yes. So, but that can that be also told as topological insulator, because that happens only in presence of magnetic field.
Right. So topological no. So that is not. So topological insulator is the one where you don't need magnetic field, and that is given by the effect of magnetic field is generated by the spin orbit coupling.
Right.
So topological insulators are one where, so this mercury telluride and all that, the material. So there you don't need to see those skipping orbits and see the age state. You don't need magnetic field the way you need for quantum Hall effect. I was just using it as a similarity of the physics which requires description of topology. Yeah, yeah.
So any other questions? Professor Bhaur, any questions? Professor Bhaur?
Professor Radha Vallabh Bhar, sir, kindly unmute your mic.
Okay, okay. No, I don't have any question. Thank you. Thank you. Thanks, Professor Ghoshal, for giving such a nice presentation.
Thank you. It's my pleasure to be part of this.
Right. So unfortunately, we started a little bit late, so probably you had to cut your talk a little bit short. But in the next session, you will get the, in the next session when we meet again with you on, I think on 14,
14th.
14, then you will get the full time.
Yeah, yeah. So,
Very interesting topic.
okay. Thank you.
Okay.
Thanks for having me. So, I will then, I don't know, is it still sharing the screen, or should I stop sharing?
It
Let
is
me
stop,
see.
sir.
Stop sharing.
Are there any
It is
other
stop, sir.
questions?
You don't have to do anything, sir.
Oh,
You
okay. 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 Yeah.
Are there any other questions from any of the participants?
Till now, no questions. All the questions have been answered. And for participants, if you have any question, you can post the question in the question answer section or in the chat box.
Chat box.
Probably there is no more question.
No, there doesn't seem to be any more questions.
Sir, we can proceed, sir. We can proceed, sir, for next.
Okay, so I think the next speaker is yet to come. So I'll just phone to her maybe. The next speaker is Professor Tanushree Shahadas Gupta. So I think he will join. I'll just phone to her.
For participants, if you have any question or you have any query, you can post it in the chat box or in the question answer section. The next session will be starting very soon. So if you have any question or any doubt, you can put it in the chat box or in the question answer section.
So if there are no questions, then we thank the speaker again, Professor Amit Ghoshal from ISAR Kolkata, for a very informative and inspiring talk, and also for giving a general perspective on the various intricate aspects of condensed matter physics that are interesting to the physics community for research right now. Right,
Thank you, Prabhupada. Thanks.
right. So please remember that he will be giving another talk on 14th at 2 p.m. Okay, at the same time, but on 14th he will be giving another talk, and the topic of the next talk, Professor Ghoshal, can you just mention?
So that will be techniques. I mean, looking into the techniques of two type. One is this inhomogeneous mean field theory to understand disordered superconductor. That's the motivation that I just mentioned towards the very end. So Bogolubov-Dejean's method, it is broadly called. So essentially, it's to deal with disordered systems. So that's one part of the talk I planned. And the second part is to talk about Monte Carlo method. So that also I wanted to spend some time. First with simple, and then depending on how much time I have, and then how much things can be packed. Because if it is so I'll try to see. But these are the two things broadly I planned. So the second topic is like this is disordered superconductors. The other method Monte Carlo will develop in melting of electron crystal or Coulomb crystal, sometimes called Wigner crystal. I mean, various different names are there, but it is a crystal without any atom. I mean, so basically just electrons will form a crystal. So that is there. I mean, people have seen that in colloids or in other places, and quantum nature of that is also found Wigner crystal. So I mean, Wigner crystal, quantum melting of Wigner crystal is not direct evidence. It is somewhat indirect evidence, isn't there? So if we want to describe that melting, I will have to devise a method, and that's what we'll be talking about. It will be mostly method, I guess. Today, I focused only on phenomenology or describing phenomenology. So there.
Okay, so that will also be a very interesting talk. So I encourage the participants to come in large numbers for that talk, and it will also be very informative and interesting from the point of view of physics, and also for learning new tools and techniques. We'll be discussing some techniques for computation which will be used, which can be used for treating these systems. Okay, so I just phone to the next speaker. She will join soon, hopefully.
Sanil sir,
Yes.
if you give the permission, then we can go for a short break for 5 minutes, sir.
Okay. But no, but if she joins,
Yes, sir,
then
yes, sir, it will be not break for participants, sir. So
okay.
that we are in the break of 5 minutes, and as soon as our next speaker joins, the session will be started.
Okay. But will this go off the air?
No, 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 sir, it will be not off. It will be
Okay.
on.
Okay. Okay.
Yes, sir, so that few people can have the drink water. Yes, sir.
Okay. 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 That's what it is. Okay. Yeah, that is fine.
So Prabhuddha,
Yes.
uh, I may not be here all the time. I mean, I will try to be part of this, but I may not be present all the time.
Sure. Sure.
So in any case, I will see you on 14th. Yeah, 2 o'clock.
Sure.
Okay. So what is showed in speaking on? I didn't. I don't.
He did not give me the topic of his talk, and he was not picking up the phone yesterday. So I don't know what is. I got the abstract from all the other speakers. Okay. Okay. So we welcome Professor Tanushree Shahadas Gupta from SN Bose National Center for Basic Sciences, Kolkata. So I will just read out her CV and I will introduce her. So Professor Shahadas Gupta works in the area of computational condensed matter physics, material science, and a major thrust area of her research is the application of first principles electronic structure calculations to understand the physics and chemistry of novel and complex materials. Can you hear me? Uh, Madam, am I?
Tanushree ma'am, can you hear us?
Adam, can you hear us? Okay. But Prem Kumar, you can hear me, right?
Yes, sir. Yes, sir. Yes, sir.
Okay.
Yes.
So,
Tanushri, ma'am. Hello.
Yeah, yeah, I can hear all of you.
Yes,
okay.
ma'am. Yes, ma'am.
Okay. So, Professor Tanushree Shahadas Gupta, she obtained her PhD degree from Calcutta University in 1995. She was a postdoctoral fellow and a visiting scientist in Onera, Paris, CNRS, uh, Clergy Pontoise in France, and also in Max Planck Institute, Stuttgart, Germany, and IISc Bangalore. Professor Shahadas Gupta joined SN Bose National Center as a lecturer in 2000. He is currently senior professor and dean in the same institute. And in between, she was Satyendranath Bose Chair Professor at Indian Association for Cultivation of Sciences and head of the School of Mathematical and Computational Sciences. He has so far produced 14 PhD students and published more than 250 research papers. He is a fellow of American Physical Society, the World Academy of Sciences, Indian Academy of Sciences, National Academy of Sciences India, and West Bengal Academy of Sciences. He is a recipient of Swarno Jayanti Fellowship, MRSI, ICSC Superconductivity and Material Science Annual Prize, BAE Raja Ramanna Prize, P. Shield Memorial Award, Dr. APJ Abdul Kalam HPC Award, and J.C. Bose Fellowship. So she headed the Max Planck India Partner Group, Advanced Material Research Unit, and Thematic Unit of Excellence on Computational Material Science at SN Bose National Center. So with that, I leave the dais to Professor Tanushree Shahadas Gupta to present a very interesting lecture.
So I am sharing my screen. Please see, tell me if it is visible to you.
Yes, it is visible.
Okay. So thank you very much for this introduction and thank you for the invitation. Just let me know in case something is not visible, not heard, or if you don't understand something, please interrupt me at any point of time. So I have a rather general title, which is the understanding and prediction of quantum materials via modeling and computation, and which I hope to do in the next hour is to, with some specific example, try to demonstrate to you how actually this understanding and prediction is done in our group. So, as Prabhupada said, that I belong to SN Bose National Center for Basic Sciences, and I belong to the Department of Condensed Matter Physics and Material Science, and I am also coordinating the thematic unit of computational material science in SN Bose Center, and the primary funding comes from Department of Science and Technology, India. And quantum materials, that's a worldwide effort on this. CIFAR, which is basically a funding agency in Canada, that actually puts really great minds from all across the world, like Seamus Davies, the famous STM person from Cornell, Anton George from College de France, Richard Green from University of Maryland, Mackenzie Manhart, both from Germany, one from Dresden, one from Stuttgart, and Tagegi also from Stuttgart. So you can see a variety of famous scientists from across the world and across many disciplines. Like Haide Tagagi is a solid state chemist. while Manhart is a person who works with MBE and PLD and makes heterostructures. Similarly, Mackenzie is an experimentalist, while Anton George is a theoretician. So basically, it covers various disciplines. And with one common goal is to come up with quantum materials, with new materials and new phenomena of this quantum materials. The other example is the Max Planck UBC, University of British Columbia and University of Tokyo Center. So three of the institute has come together to make one institute on quantum materials. Of course, NSF has put lot of money and effort on this direction. I would just mention only one, which is 2D Crystal Consortium that actually involves many different institutes in US. So in a nutshell, there is a worldwide effort in the topic of quantum materials, and that is considered to be the research area in the near future. And just to mention, India is not, although there is a late entry, but India is also considering it as one of the research topic for the future. So, for example, in the latest budget speech of our finance minister, a large budget of in the tune of 80 billion rupees over 5 years have been announced as a part of new national quantum mission. So therefore, it's coming up in a very big way. Well, so the quantum technology, it can be possibly realized in superconducting loops using trapped ions, silicon quantum dots, topological qubits, the diamond vacancies. So there are many possible platforms that has been discussed. However, all these technologies at heart, it depends on materials, because information is physically encoded in materials. So there is a huge role of materials design. So then the quantum technology platform development, on the way to this development, the new physical concepts, phenomena, functionalities, and materials are being explored. So the workflow is the following. So I have a theoretical concept. Let's take the example of Majorana-based quantum computation. And the concept realization depends on having systems like topological superconductors, superconductor ferromagnetic interfaces, oxide interfaces. And that is actually dependent, as I mentioned, and put a stress on it, on the materials designing, because shortlisting of this candidate is one of the important goal. And once such a designing is kind of perceived, it will be referred to for laboratory growth and characterization. So we have a really a complete loop of different workflow. So, well, the importance of materials, I don't think I need to convince the audience on this. It is so much so that each of the ages in human civilization have been named after one material or another, starting from the Stone Age to Bronze, Iron Age, Plastic Age, and to the modern age of the Silicon Age. And it was actually the farsightedness of the Italian painter and philosopher Leonardo da Vinci who actually envisioned that the future age is going to be that of a designed materials age. So the quote from him is, when nature finishes to produce its own species, man begins using natural things in harmony with this very nature to create an infinity of species. And what are quantum materials? Of course, all phenomena, if you are really going to t equal to 0, this is dictated by the laws of quantum mechanics. So all materials are quantum materials. However, we are talking really about the materials which even at finite temperature basically exhibits property whose descriptions are governed by the laws of quantum mechanics. So for example, take the example of superconductor, which is showing the zero resistance at a finite temperature. That happens at finite temperature. And taking the modern example of high TC cuprates, even in the tune of hundreds of Kelvin, there this phenomena is governed by the laws of quantum mechanics. So that I actually mean by quantum materials. So the properties which even at finite temperature are dominated by quantum fluctuation, quantum entanglement, coherence, topological behavior, which are all manifestation of quantum mechanical effects even at finite temperature. So understanding and prediction on quantum materials is actually very vast and very broad. It starts with variety of expertise like synthesis, characterization, design, fabrication, prototypes, and one of a major component in this entire workforce is that of modeling. So this involves various branches of science, the nanoscience, mesoscale science, advanced instrumentation, material synthesis, which is actually a very important component, and modeling and simulation. So we will focus in my talk in this last aspect, that's the modeling and simulation. Of course, it's a hand holding between experiment theory and simulation. The modern science basically relies on these three pillars that holds the entire concept. And as I mentioned already, we will focus on the simulation aspect. So there have been a lot of effort also in India on theory supported computation, and the backbone are the high performance computing, and I have shown a typical components of such a high performance compute clusters. And there are in our country several places where we have 100 teraflop or larger capacity high performance compute cluster. I have just given some representative names like JNC, IISc. In Kolkata, in SN Bose Center, we have a cluster which is of the tune of 150 teraflop capacity. ISCS, IIT KGP, CDAC, ISA Pune, and the list is actually more than what I have listed here. And in recent time, there has been a huge effort in the name of National Supercomputing Mission, which is aimed for having petaflop machines under this mission. And already such machine has been installed in CDAC, ISA Pune, and IIT KGP, IIT Kanpur, as well as JNCSR. And there have been also some discussion to have such a kind of effort in Kolkata. Of course, we will be all beneficiary if such a petaflop machine is set up in Kolkata. Okay, so within this materials modeling, we will put our focus on electrons because many of the properties are actually dominated by the behavior of the electrons, simply because electrons are the glue that bind atoms together. And our goal is to calculate the electronic properties, the properties of these electrons in an ab initio or first principles way. So what is a first principles approach? So it gives a way of calculating the properties of materials before it can be tested in a time consuming and costly laboratory experiments, which actually limits materials discovery. So before you go to lab and get into such time consuming and costly experiments, the ideas can be tested and checked in terms of doing such kind of a first principles calculation. The good thing of such first principles calculation as opposed to a model study, they retain all the chemistry and the structural information in the calculation, and thereby it actually provides a microscopic understanding. And I have put a flow chart in this very briefly to tell about what is a first principles calculation. So one basically starts with the structural information, which can be either obtained from experiment or by doing even a structural optimization.
Volume is becoming low.
Yes,
The volume is becoming low.
it's
Increase volume.
becoming low. If
Ma'am,
I
your voice is getting low. Yes, yes.
then it will crack. Is it okay now?
Yes, now it's so.
So basically the flow chart is the following. You start with all you need to know to do this calculation. What are the chemical constituents? What are the structure those atoms make? And with that information, what you solve is, which looks apparently like a Schrodinger equation, which is a Kohn-Sham equation, as has been shown here, except the potential here, unlike your Schrodinger equation, the potential itself depends on the electronic density. So the electronic density, which is supposed to be the output of this calculation, is actually input, because the equation I'm trying to solve, the potential depends on the density. So therefore, this is done on an iterative way. You start with some assumed density, and with that you build the potential through solving a Poisson's equation, get this Kohn-Sham equation, and solution of this Kohn-Sham equation gives you basically the information of Kohn-Sham orbital. And once you have those Kohn-Sham orbital, you can get the density corresponding to those orbitals, which are basically, since it's a density functional theory, everything depends on density. With that, you calculate the energy, and you keep on doing that until and unless the energy between two successive iteration is less than some small number. So what are the quantities you can calculate out of such first principles calculation? As I mentioned, is the structural stability. You can calculate, this method is very good in calculating the total energies, and the difference of the total energies comes out quite accurately. So therefore, the structural stability can be very accurately studied within this method. You can calculate the band structure, which is basically the energy versus wave vector, the dispersion. And since you have access to the band structure, you can calculate the optical properties. You can calculate the phonon, both in harmonic and quasi-harmonic approximation. Therefore, you have access to free energies like the Helmholtz and Griggs free energy. In principle, these are all T equal to 0 Kelvin calculation, but you can handle the finite temperature through a method which is known as ab initio molecular dynamics, which quantifies quantum mechanics with molecular dynamics, in which the electronic degrees of freedom are handled by solving the Schrodinger equation or the Kohn-Sham equation, the Schrodinger-like equation, while the ionic degrees of freedom are solved by classically by solving the Newton's equation. These two things, the electronic and ionic degrees of freedom, being connected to each other by Hellman-Feynman force, which is completely quantum mechanical force. So although the ionic degrees of freedom are solved in this method by solving Newton's equation, which is a classical equation, the force which each of these ions experience are calculated in a completely quantum mechanical way. Ability to handle strong electron-electron correlation, well, within certain approximation and within certain model approach, you can handle this strong electron-electron correlation within DFT plus U, which is like a static mean field approximation. Of course, the dynamical part of the strong electron-electron correlation is not included, but many of the cases, especially if you have magnetically ordered system, such a kind of naive DFT plus U-like approach actually works pretty good. So the first set of problem that I will discuss is how can you employ such method in understanding materials property. What I mean by that is a structure property relation. So the output of any standard density functional theory code is what is shown here, which is basically spaghetti of bands. It is energy versus the wave vector plotted along the high symmetry points of the Brillouin zone. And as you can find, this band structure is complex, rarely interpreted, and one needs a filtering for this to be useful. And the filtering that we will use, as I will try to convince you with some demonstrated example, that this gives a very convenient way to come up with models, but ab initio derived model. And since they are ab initio derived model, this provides you with the means to add chemical reality to physicist model. So basically what is shown here, instead of the words, let me just explain to you in terms of pictures. So this in red, what is shown is basically the band structure that comes out of a density functional theory code. The zero of the energy here is set at the Fermi level. And you see at the Fermi level, there is only one single band that is crossing this Fermi level, which is shown with the blue. So what this method actually does, given this red colored band, it provides you with this single blue colored band that has good matching with the red colored band within an energy range of, let's say, plus minus 1 electron volt around the Fermi level. So that is basically gives me the low energy physics. So the whole idea is to come up with an effective band structure which matches the full band structure within a narrow energy window around the Fermi level. And what is shown in the right-hand panel is the wave function or the one-year function that basically describes this single blue band. And as you find that this wave function is pretty long range, you have in its center, as I'm showing with my cursor, the center has like a copper. It's made out of copper. The band structure shown here is for a copper oxide cuprate compound. So this copper, this one single band is basically an anti-bonding band formed by copper and oxygen. So what you see that the shape of the wave function close to the origin where the copper ion is sitting is like x square minus y square. But as you move out of it, it shapes almost like oxygen P because you have these two lobes oppositely colored. But one lobe is much fattened compared to the other lobe. And this fattening comes because here, this lobe of the oxygen that basically makes a bonding or couples with copper 3s square and copper 4s. That gives this fattening. And as you move outer and outer, you see these tails which are like oxygen P's, but further and further oxygen P. So now I show you basically the phase diagram of high TC cuprate material, which is possibly known to some of you. So in the y-axis is the temperature and x-axis is the hole doping that you take these cuprate materials. So all these materials have one thing in common. They have copper and they have oxygen. So they are all copper oxide materials. So you have layers, two-dimensional layers, which is shown here, which is a single copper surrounded by 4 oxygen, and that forms like a square lattice. And that forms like a layer, and you have stacking of these layers. In between the layer, you have elements like lanthanum or bismuth or thallium or barium or mercury. So by changing those things, what you notice, and by doping these materials, you have, so if you undoped material is an antiferromagnetic insulator, and this phase, as you are doping more and more hole in this copper oxide plane, this at some point the antiferromagnetic insulating phase vanishes, and you have basically the appearance of superconductivity with a dome-like shape. And the maximum point of this dome-like shape is this Tc max, which is the maximum superconducting Tc of this material. And as you can find that for lanthanum compound, this Tc is 40 Kelvin, while for bismuth, thallium or mercury compound, this for thallium and mercury, this Tc is 90 Kelvin, while for bismuth, this Tc is 40 Kelvin. So our goal is to make this Tc higher and higher, and with a dream that one day we can make this Tc even room temperature, so that you have a room temperature superconductor. But for that, we need to understand the trend. And you find that in the trend, for even with the same copper and oxygen, just by changing this element, you have a huge variation of Tc for about like going from 40 to 90, it has become more than double. So what causes it? So this shows basically a typical crystal structure of a high Tc cuprate compound. You have, as I mentioned, this copper oxygen plane. So you have the copper atom, which is shown with the red, and that is surrounded by the oxygens. And there are some oxygens which are in plane, and there are some oxygens which are out of the plane. And what is important, which comes out of our calculation, is this distance. This is position of this oxygen, out of plane oxygen, which is also sometimes in literature known as apical oxygen. This apical oxygen to copper oxide plane, that distance is a key structural parameter as comes out of our calculation. So what is shown in the right hand side is basically again the same band structure, but now shown for two compounds. One, it is shown for the lanthanum compound, and in the other one, it's shown for the mercury compound. You again have this single band that is crossing the Fermi level, and this single band, which is shown with the red color, looks pretty similar between the two, until and unless you are an expert to see the difference. Indeed, there is a difference. You can find that at the gamma point, which is shown here as G, this red band stops somewhat, lies somewhat higher than -2, while in this case it actually goes pretty below -2. But it gets reflected if you calculate the Fermi surface. The Fermi surface here is shown as an insect. So you find this Fermi surface, which this is the 0, point. This is gamma, this is pi 0 point, this is 0 pi, and this is pi. So the Brillouin zone of a square lattice is also a square. And you find that the Fermi surface is, in case of the mercury compound, there is a big difference. It actually gets turned around and it gets centered around the pi. While in case of the mercury lanthanum compound, it's much less turned. It's unlike in the mercury compound. So there is a big difference between the Fermi surface of the lanthanum compound and the mercury compound, which comes basically the fine difference of this red band structure that is shown here. Even more evident is the wave function that describes this red band. You find in case of the lanthanum compound, just compare it with the mercury compound. The mercury compound is far more delocalized, while the lanthanum compound is much more localized in plane. So from here, what you can define is a range parameter of this wave function. And just from this picture, you can imagine that the range parameter for lanthanum compound and mercury compound are quite different. The range parameter of the mercury compound being much larger than of the lanthanum compound. So on the y-axis, this range parameter is plotted as a function of this copper oxygen plane to apical oxygen distance. And you find really there is a kind of a nice scaling between copper to apical oxygen distance to that of the range parameter. What we did, what I showed for the lanthanum and mercury compound, we basically did it for all known high Tc cuprate. And what we found that in the x-axis, you have the same range parameter, but in the y-axis, what we have plotted is basically the Tc max, which is measured experimentally. So in a way, this is like a semi-empirical plot because the x-axis is our calculated quantity, while the y-axis are the measured TC max. And what you find is we did it for many, I mean, instead of a single layer, 2-layer, 3-layer material. And if you follow just the black dots, you will find a correlation between this range parameter and TC max. So what this density functional theory helps is to filter out a single quantity, which is this range parameter, having a correlation with the TC max, and this range parameter being dependent on a single structural parameter, that is copper oxygen to apical oxygen distance. The next example in this category that I would like to demonstrate is that of the low dimensional quantum spin system. These are the transition metal oxides or chlorides with small spin. What I mean by small spin is like copper 2 plus, vanadium 4 plus, or titanium 3 plus that has a single electron. In case of copper 2 plus, it's a single hole. So therefore, the spin associated with it is half. You can take also nickel 2 plus or vanadium 3 plus, which has 2 electrons or 2 holes. Therefore, S is equal to 1. So therefore, the spin is small. And although all these compounds are three-dimensional compounds, important magnetic interactions are in 1 or 2 dimension, and therefore is the name as low dimensional. So although structurally they are three-dimensional, but magnetically their dimension is less than 1 or 2. And this provides a fascinating playground to study properties which can be dictated by quantum fluctuation, like a spin gap state, spin charge separation, quantum criticality, and superconductivity. What is important for us, often the true nature of this exchange network, that means what are the dominant magnetic exchanges, which magnetic exchange path are there. That is not just what you expect by looking at the crystal structure. So this calls for the microscopic investigation by coupling the ab initio and many-body method. So there are many effective models like a Harvard model, I mean, where you have basically the interplay of the kinetic energy term and the strong on-site correlation term, which is defined by these two parameters T and U. From here, if your U by T is much larger than 1, or U is much larger than T, you can derive a model by integrating out or projecting out the double occupancy is that of the TJ model, where instead of U in this model, you have the J, which is the magnetic exchange. And if you are really at half filling, then the hopping is not possible because every site is occupied by one electron or one hole. In that case, your TJ model boils down to Heisenberg model with these magnetic exchanges, Gij, which we are interested in calculating. So as I said, so the idea is you start with the density functional theory, do the electronic structure calculation, then do the downfolding. Therefore, you can pick up only the bands which are close to the Fermi level, add the electron-electron correlation, come up with an effective spin model, and then you use a many-body method like exact diagonalization, QMC or DMRG to arrive to a physical picture. And we have done it for many compounds, and by calculating the magnetic susceptibility, which can be indeed compared with the measured magnetic susceptibility, or calculating the spin wave spectrum, which can be actually compared with the neutron experiment. So here I take the example of a 1D spin chain. So that means these systems are three-dimensional, but their magnetic interactions are such that they can be, in terms of a spin model, they can be considered as strictly in one dimension, having the interaction, chain-chain interaction being negligibly small. So you can have a uniform Heisenberg antiferromagnetic chain where you have basically the interaction between two neighboring spin to be antiferromagnetic. You can also from here derive a situation where you have an alternating chain compound so that you have an interaction J1 and J2 and it kind of alternates between the two. And of course, with some alternation, you can actually show that it opens up a spin gap within your spin excitation spectrum, meaning your ground state is a spin singlet ground state, which is separated by a gap to the spin triplet. You can also have a situation where in addition to nearest neighbor magnetic interaction, you can have the next nearest neighbor magnetic interaction, like a J1, which is a nearest neighbor, and a J2, which is a next nearest neighbor. And that phase diagram has been already solved with variety of techniques, and you have a famous Majumdar-Ghosh point where this ratio of J1 by J2, that's 2, then you actually have a dimerized gap state. You can also have some short range gap situation. So the question that we asked, what happens in presence of both alternation and nearest neighbor interaction? Like you have a J1, J2. Also, in addition to that, you have a nearest neighbor as well as next nearest neighbor interaction. For that, one must identify a compound which shows heavily suppressed interchain interaction, excluding formation of any three-dimensional order, and significant next nearest neighbor interaction, as well as alternation. Well, I think the solid-state chemists have done great job. They came up with this compound, which is where the magnetic ion is the copper, as it's shown here, and it has a zeolite-like structure. You have basically like a sheet-like situation where you have two copper 1 and copper 2, which are in square planar coordination by oxygen atoms. As is shown here, 2 unit, copper 1 and copper 2. And then you have the chains of this copper 1, copper 2 like this. And 2 chains are connected by this AlO4 tetrahedra, as is shown here. And that makes like a sheet. Then you roll down that sheet, and which forms a cavity containing structure like this, and the cesium atoms are placed in between the cavity. So if you really look at it, so the structure is the following. As I said, you have copper 1 and copper 2, and the squares, they basically H share. So you have copper 1 and copper 2 connected by through 2 oxygen to each other. And then you have basically copper 1, copper 2, copper 2, copper 1. So this is, and the angles are shown here. And as you can find out, these angles are very close to 90 degree because they are being shared. So that actually makes the situation even more interesting because you have the possibility of both ferro and antiferro interaction. And we did the DFT electronic structure, and if you do a non-magnetic calculation, of course, you will get a single dx square minus y square band, which is half filled. If you make spin polarized, that opens a tiny gap. If you do a DFT plus U, as I mentioned, then this gap value increases. So what we found is a very interesting thing. Since it is a H-shared situation, the nearest neighbor hoppings, the effective hopping between copper x square minus y square and another copper x square minus y square, which is placed in the neighboring site, you find that they basically, their tails cancel each other because they are H-shared. So therefore, the nearest neighbor hopping T and T prime, T is between copper 1 and copper 2, T prime is between copper 2 and copper 2, that is smaller compared to next nearest neighbor hopping. There are 2 such, T and T prime, the next nearest neighbor. That's because they point towards each other, all these tails. So therefore, the model you have is basically T, T, T prime, T, T, T prime. Instead of T, T prime, there are 2 T and 1 T prime. And in addition, you have a T next nearest neighbor and T prime next nearest neighbor model. And these are the parameters which are being given. So it is a fairly complex model Hamiltonian, which has a nearest neighbor J term, alternation to J prime. We set J nearest neighbor and J prime nearest neighbor to be the same because their hopping values are pretty comparable. And what was interesting, we find the J prime to be antiferromagnetic while J to be ferromagnetic. This is complex Hamiltonian due to the inherent frustration effect you have in this one-dimensional model. So we solved it with quantum Monte Carlo, and because of the inherent frustration effect, of course, this is a notorious sign problem. So to avoid that, what we did is we considered for J prime only the SZ term, omitting the spin raising and spin lowering part. And that showed a reasonable agreement with the experimental susceptibility, which is shown with the dots or circles. And the estimated spin gap we found to be about 3 Kelvin. Since we had to really consider a simplified Hamiltonian within the QMC, we did an exact diagonalization calculation and we varied even the J and J prime, fixing 2 different values of the second nearest neighbor hopping. And what we found that it might be even possible to drive the system gapless just by playing with this parameter, and hopefully by taking this compound and making it like in a film form and putting it through some piezoelectric, through which your strain can be controlled. Maybe one can play around with these parameters and to have a quantum phase transition from a spin gapped to a zero spin gap transition. So I hope with that we have proved that such kind of the first principles calculation to be an effective tool in uncovering the structure property relationship. Before I get into the next section, are there questions?
I think there are questions, but normally
Yes.
we take the questions in the question answer session at the end.
No problem. If that is the format, then I will continue. So the second class of problem that you can handle with such technique is the prediction of new functionalities in known materials. So the first kind of problems I talked about, where you know the functionalities, you also know the materials, you basically discovered some structure property relationship, properties have been measured and materials are known. Now we get a little more ambitious and try to make some prediction of new functionalities in known materials. And for that, the example that I will discuss are the metal organic complexes and coordination polymers with a spin switchable functionality. So what exactly I mean by that, these are the complexes where you have at the center transition metal ion. Very often this is iron 2+ ion with the D6 configuration, which are connected to organic ligands. And since they are organic ligands, they are flappy, they are flexible, and they can be manipulated using several different techniques like light, temperature as is shown here, through some pressure, which can be chemical or mechanical pressure, substrate, or magnetic field. So when you are at low temperature, So as I said, this is iron 2 plus. So therefore you have a D6 configuration. And because of these ligands which are attached, or the chemical molecules that are being attached, you have a octahedral crystal field around this iron 2 plus ion that splits the 5 different degenerate iron levels into T2G and EG. So at low energy, at low temperature, when this iron to this bond, to this ligand bond length is small, this energy difference between T2G and EG is small. So therefore, the favored configuration is when I put two of these electrons paired up, all paired up in the T2G level, having a spin, total spin of 0. Now, if I heat up this material, what happens, basically all this bond length, they expands. As a result of that, what I have, this T2G EG energy level difference actually shrinks, and it becomes then convenient to have a Hund's rule guided ground state, in which case I take two of this blue colored, green colored arrow and put them at the higher energy EG states. That's exactly. So that means you have a spin state transition from S equal to 0 to S equal to 2, which is driven completely by temperature, by external means. And this is going to happen for any transition metal ion having an occupancy between D4 and D7. You can work it out in an octahedral environment. Now the idea is, can we make such a kind of, this is still a spin crossover. It's a crossover from one spin state to another spin state. Can you make this transition cooperative? That means by, instead of having one molecule, you put many molecules next to each other and make like a polymer. In such a case, such spin transition becomes cooperative if the interaction between two molecules exceeds certain threshold. And such a case, your spin state transition from a low spin to high spin can show up with an hysteresis effect. And there is a huge importance of such hysteresis effect, because then your molecule remembers whether it was in low spin or high spin state, depending on whether you are in cooling path or heating path. And then you can use this material as memory devices. So the whole idea is, can we devise such a molecule which is having a large hysteresis? We need to be operative, to be used in commercially, you need actually this hysteresis to be large, and the central point of this hysteresis to be close to room temperature. So this is what I have shown here, this bistability. Actually, your crystal changes color going from low spin to high spin, because the associated band gap also changes. And so especially important in these materials is the large cooperativity, in contrast to a molecular crossover system. So from molecule, we want to make it like a polymer. So what are the possible candidates? As I already mentioned, one possibility can be to work with coordination polymers, which are built by putting one molecule to another molecule, and they can be made connected in all three dimensions as is shown here. This is also although this is shown in a nice, artistic way, but actually this compound has been made, and I'm going to show one slide on this compound where it is a three-dimensionally connected coordination polymer. The other possibility are that of the hybrid perovskite. We have all aware or known of the perovskite structure, which is of formula AbO3. So the idea is, instead of a cation, which is can be calcium, strontium, barium, replace that with a molecule, as is shown here. Similarly, you can replace this oxygen, which is an anion, by a complete molecule like formate. So these materials are known as hybrid perovskite, which have been discussed quite a lot. in context of solar cell. These are lead based hybrid perovskite, but here we are considering transition metal ion based hybrid perovskite. So these are challenges, although technologically they are very important. These are challenges for material specific predictive theoretical descriptions, because we are handling with transition metal ions. So therefore the strong electron-electron correlation in open D shell of the metal center becomes important. The complex geometry of this material, these materials can be very complex, having about some 300 to 400 atoms in the unit cell, which actually pushes us to the limit in which we can handle such big system. And this also needs the ability to capture the electronic and structural changes that happen under external perturbation. So the methodology that we used is DFT plus U to handle the strong correlation, coupled with an ab initio molecular dynamics, because we want to see the temperature induced changes in the system. So we have worked on this hybrid perovskite, as I already mentioned, and there as an external perturbation, what we actually did is we used the pressure, the hydrostatic pressure, and just by changing this central ion, which is shown here, we can not only change the critical pressure that is needed for such a spin state transition, but we also had a huge change in the hysteresis width simply by changing both these compounds are iron format. So that means I have the iron as transition metal ion, which is at the center of this octahedra. Instead of an oxygen, I have a format which is HCOOO, which is shown here, at the central part, which is basically substituting for the A cation of the inorganic perovskite. These are amine, these are protonated amine, and just by changing this functional group, we managed to show a huge change in the hysteresis width. The other one is the example of the coordination polymer, like a linear chain. And these are the results of the ab initio density functional theory. What we show is basically the free energy as a function of magnetic moment. So at T equal to 0, the low energy state is stable. At high temperature of 200 Kelvin, the high spin state becomes stable. We also found a bistability, which actually matches quite well with the experimental temperature, having a bistability of low spin and high spin. And by plotting the high spin fraction with the temperature, we also could actually derive this hysteresis curve, which shows a very good agreement with the experiment. I told you that I wish to talk about this artistic, which looks like artistic presentation. These are basically bimetallic coordination polymer, where you have iron and niobium. Niobium has one spin, but it doesn't show any spin state transition, while iron shows. So this compound has been synthesized, but its spin crossover properties have not been really measured, the temperature and pressure dependent properties. And what we did by applying both temperature and pressure within our computation, what we came up with is basically four different states of this compound. One possible state is which we labeled as HS1. We have the high spin state of iron, where the spin of the iron is anti-parallel to the spin of the niobium. The high spin 2 state, where the spin of the niobium becomes parallel to the spins of the high spin iron. The intermediate spin state of iron, we may achieve the new spin state of the iron, which is the intermediate spin state, which is the S equal to 1 state, with parallel orientation of niobium spin and of course the low spin. So in this temperature pressure phase diagram, we achieved the new spin state of iron as well as tuning of magnetic or exchanges between iron and niobium, changing it from anti-parallel to parallel. So these are, of course, our prediction on some materials which has been synthesized, which exist. So I do hope, and we hoped with that, that following our study, since these materials are already synthesized, their properties should be measured and some novel functionalities can be discovered in the lab. So that's basically designing of new functionalities using such an ab initio technique. So with that, I come to the last kind of example. Can we predict new material altogether? We definitely need new materials with targeted properties. So now we are back to almost Leonardo da Vinci, where he thought that we can actually predict new materials which doesn't exist in nature. And I have special interest on magnetic materials because of their enormous technological importance. They have been discussed heavily. However, there are also some magnetic materials which are special, like ferromagnetic half metals. What I mean by that, so where your carriers are 100% spin polarized. So that means the carriers are having only one specific spin polarization. Or in other words, in one of the spin channel, your compound is conducting, while in the other spin channel, it's completely insulating. So that has a tremendous application to spin valve effect, central to magnetic storage and sensing, and gave rise to defined a complete field like spintronics. And another important materials are antiferromagnetic metals because they can be used as spinning layer in such a spin valve device. However, these are actually rare. All these are rarities. Both ferromagnetic half metals and antiferromagnetic metals are extremely rare in nature. Most ferromagnets, though metals, are not half metals, and most antiferromagnets that we know of around us are insulators, they are not metals. So we need new materials with these targeted properties. And for that, what we chose as our area of exploration is that of the double perovskite. So I mentioned of perovskite, which is of the formula AbO3. You double this formula so that it becomes A2B2O6. Since I have B2 instead of one transition metal, as in conventional perovskite, I can play with two different transition metals, namely B and B prime. And what is shown here, if you are fortunate and if you are a good solid state chemist, you also know how to make B and B prime order. So therefore, I have this blue octahedra, which is this, let's say the B prime ion surrounded by 6 oxygen. And then I have another BO6 octahedra, and they alternate in all three directions. That is what is known as double perovskite. Why did we thought of taking this particular family? That is a plot of magnetic transition temperature in many of these double perovskite compound, and you find that many of them are above room temperature and something which are even exceeding 600 or 700 Kelvin. This is a very nice review article from Vasala, which came up in Progress in Solid State Chemist. What they did, they fixed basically the ion at the A site to calcium, strontium, barium, and lanthanum. In fact, only these four has been used to put in the A site. And then what they did, in one axis, they have different possible ions that can be put at the B side, and in the other axis, they have other possible transition metal ions that can be put at the B prime side. So you can see that will give rise to huge number of possibilities. What is marked with the green boxes those are the compounds that have been already synthesized. What is shown with the red, where attempt has been made, but it failed. The ones which are shown with the yellow color are the compounds which have been synthesized, but they have been synthesized under high pressure and temperature, so they need special treatment to synthesize them. While the violet ones are the compounds, they have been synthesized, but unfortunately they show non-perovskite structure. But what I want to draw your attention that there are many white boxes. That means those has never been attempted to be made, and nobody knows if that has been made, what their properties would have been. So a lot of properties yet to be explored. So can one use machine learning for this purpose? Of course, this is some jargon which has been used quite often in recent time, but I think there is some potential in this method if can be used appropriately in conjunction with other methods. So that's a Nature article which actually poses this question. Can artificial intelligence create the next wonder material? Well, the method is the following. This is basically nothing but a pattern recognition. So for that, you build up a database. So we built up a database taking into account all different double perovskite compound. We considered only the divalent cation at the A site, that means calcium, strontium, and barium. That gave me some 641 compounds that have been so far made based on calcium, strontium, or barium at the A site. Then of course you need to do something which is known as data pre-processing, because some of the data are very atypical. These are like outliers which you need to eliminate from your database. Then we characterize each of these data point by an attribute. As I said, this is like a pattern recognition. So how do I recognize somebody as Indian? So we might say by the food habit, by the skin color, by the kind of dress they wear, something we have to characterize with, and that characterization things are like called attributes. And once we have these two things like a database construction and the through instances, which are known as instances, each of the data point and the attributes, you find your favorite model, which is basically a machine learning model, which is a pattern recognition model. And then you come up with prediction of new compounds. Just to give you an idea, in our case, the attributes are, some of the attributes are structure related, like the ionic radius of B and B prime cation, their differences, a tolerance factor, which is actually shown here, which is related to the ionic radius of A cation, oxygen, B and B prime. The others are chemistry related. At this point, we did no calculation. I would like to mention no calculation. Their valences, their column position in periodic table, their row position, atomic mass, electronegativity, atomic number, all these are available. You don't need to do any calculation. So these attributes should be something which are not calculated quantity, which are all available in your periodic table. And through this machine learning mechanism that I have already mentioned, we scanned 412 combinations, new combinations. Those were like your white boxes. And we found out of all these combinations studied, 33 are strongly predicted as double perovskite, 60 with a moderate confidence, because each of the prediction in this machine learning comes with a confidence level. So for sure, we can say that these 33 compounds, if made, they will be double perovskite, they can be synthesized. For 60 compound, our confidence level is low. We also for certain said 54 compounds which cannot be made. For 29, our method failed. So out of that 33, we then made a crystal structure prediction, because for any compound you have to tell what are their crystal structure, because since they have never been made. And for that we used a genetic algorithm, and which is basically, you start with few initial structures which we started with, which are basically the crystal structures in which double perovskites form. And then through energy calculation, you pick up from there some of the low energy structures that makes a parent. From there, we use uh, operations like recombination, mutation, that generates the next generation crystal structure. Then again, we select them by calculating the energy. Then that defines a new population based of the old and based of the new structures, which is all based on your energy consideration. And then this entire loop is basically executed, so to come up with the best possible structure that comes out of the genetic algorithm. So these are the different crystal structures we predicted, and when we plotted them as a function of tolerance factor, these actually agrees pretty well with the common knowledge that you have based on the tolerance factor and the structure. We didn't stop there. We calculated their electronic and magnetic properties. These are the calcium-based compound, strontium-based compound, and barium-based. And we actually discovered a plethora of electronic and magnetic properties, some as ferrimagnetic insulator, some as ferromagnetic half metal, which we were looking for, and antiferromagnetic metal. We got some as antiferromagnetic insulator, ferromagnetic metal, as well as non-magnetic. So with that, I feel we have basically predicted a large number of double perovskite compounds, which now the experimentalists can take up, synthesize, and really validate our prediction. So this material matters, and new materials in design should be one of the slogan of the next generation, and it's a playground for the future. And of course, I didn't do all this work by myself, that I presented acknowledgement to numerous students and collaborators. Thank you very much for your attention. I'll be happy to answer if there are questions.
Okay, so thank you, Professor Tanushree Gupta, for very informative and interesting presentation. And so now the session is open for questions. So I think Mr. Uttam, no.
Participants are requested to kindly ask any questions, or if you have any doubt, you can ask.
Should I stop sharing?
Yes, you can stop sharing. So,
now there is a question answer session, so it is requested to all participants that if you have any questions or you have any query, please ask your question by putting the question in the chat box or in the question answer section, or you may raise hand. So this is the question answer session, so participants are requested to kindly ask any questions if they have any doubt.
okay, so I have one question, which is that you said that using the machine learning, you can shortlist some of the compounds to double perovskite structure, and then you can use the evolutionary algorithm like USPEX to find out what exactly is their actual structure and then calculate their properties using evolution. But what if after you have shortlisted them as double perovskite, then when you use the USPEX, you find that they are not actually double perovskite structure, but they are coming out to be columnar or some other structure?
Yeah, so that is a very good question. In fact, we never came across something which, according to our prediction, is a double perovskite, but we found them to be columnar or something. Because as opposed to just blindly calculating their structure, we use the machine learning, and in that machine learning, we had basically the information of double perovskite or non-double perovskite. So that means that information we have in our database, all these compounds have been made. And some of them are in the double perovskite structure, majority of them. But we also had an information that some of them, although they have been successfully synthesized, but they don't form in double perovskite structure. So for us, no means two possibility. Either it cannot be synthesized at all, or if it can be synthesized, it will not be in double perovskite structure. So for me, the no means it is a non-double perovskite structure, or it cannot be synthesized at all. And I didn't actually had time to go through the details of the machine learning, but the number of cases in our database which are double perovskite is much more than the number of cases which are non-double perovskite. So therefore, we actually used a cost sensitive algorithm, because the cost that you do for being double perovskite and non-double perovskite are not the same. So to cut the long story short, your answer to your question is, through machine learning, we basically select those combinations which will give me a double perovskite structure if made.
By looking at tolerance factor and all these things?
No, those things are already in your feature, which we called as an attribute. So tolerance goes as an attribute already.
Okay.
So as I said, this is like a pattern recognition. So if I say that this combination has these attributes, by pattern recognition, I can already tell that, okay, if made, it will form in a double perovskite structure. It will not be a columnar or any other structure.
So, Professor Bhatt, do you have any questions? So let me introduce Professor Radhavallabh Bhatt is our head of the department.
Okay.
Department of Applied Sciences.
Okay, thank you, ma'am,
Thank you.
for giving such a nice lecture, and particularly different area, computational material science. You have given a elaborately how to gradually we can approach towards the material fabrication by getting some idea from the basic idea from the computational way, because obviously you have mentioned that experiment is very costly. So before going to any experiment, if we see that what are the possibilities, and we can minimize the number so that we can go for that particular type of material or experiment, then we can success rate maybe relatively low cost. Otherwise, what will happen empirically, if we start one by one select and start to make experiment, then it will be difficult to get it, and that will become very costly, and that is sometimes it is impossible. So it's
Yes.
a good basic idea or direction what we have given to our participants, to us also, so that they have got a lot of information from you. And thank you very much. And we have gathered, and our participants also gathered a lot of knowledge from you. And thank you very much on behalf of us, on behalf of the department and behalf of the university, for coming over here and spending some time for us. Thank you.
Sure.
Thank you.
Thank you.
Okay, thanks, Professor Bhatt, for your right comments. And so, are there any questions from the participants? Question answer, I can see something, but this is for the previous speaker?
No, no, there is no question now at this moment.
There doesn't seem to be any question from the participants right now. Okay, if that is the case, then let us thank once again Professor Tanushree Shahadasgupta, Senior Professor of SNGO's Research Center, and for a very interesting and informative talk, and also on enlightening us on how to make new materials, and also on various aspects of two-dimensional magnets and also ITC superconductors, how to increase the TC, etc. So it is a very informative talk, and I hope our participants can take away a lot of important points which will be beneficial to them for their further career development and also for their research in areas of physics. So
At one, I just want to mention that if somebody has some question, even at later point, they may not be ready to ask now, they can always email me. You can share my email with them.
sure, sure. I can share the email and they can email. We conclude this session today. In that case, and tomorrow the next session will again. Okay, I think there is something. Chat box.
Yes, so we have provided the feedback. Yes, sir.
Exactly.
So tomorrow again the session will start at 2 p.m. And tomorrow I think we have as speakers Professor Vikas Das and Professor Saurabh Chandra, right? I think so.
Yes, sir.
Yes, yes. Yes, Vikas Das and Saurabh Chandra.
Yes,
Vikas Das from Aizat Tiruvananthapuram and Saurabh Das from Aalto University, Finland.
right, Saurabh Chandra. Okay, so
Yes, yes.
Okay, thank you then.
thank you, madam, for attending this session and giving us a very nice and informative talk. So we conclude this session today with a thanks to all the participants and to all the both the speakers, both the eminent speakers of this session, Professor Amit Ghoshal and Professor Tanushree Shahadasgupta. And also we thank Professor Radhavallabh Bhatt and Professor Somadar, who the director of the School of Natural, Applied and Social Sciences, which is actually hosting this event, and MAKAUT, and also our Vice Chancellor, Honorable Vice Chancellor, Professor Shoikat Moitro, who inaugurated the session of the FDP. Okay, thanks to everyone.